Welcome everybody. We'll start our session this morning with a couple of forecasting talks. First up, we have Dave Gochis. He's a friend of ASO. He works at NCAR. He's been working with us since about 2015, where I think we started in Colorado, in the Rio Grande specifically. And this year, he's expanded his forecasting out to California. So ingesting ASO data and running the forecast forward. And so I'm really excited to hear Dave's wrap up today. Okay.
Let's see, so I'll go ahead and share.
Please do.
Let's see, come on now. All right, that went into full screen, I hope.
Yes. Yes,
okay.
You're all good to go.
All right, so yeah, thanks a lot, Kat. As Kat said, we've been working with the ASO team here for several years now, but only in the last couple of years have we really sort of gone into this operational world doing ASO assimilation in real time. And that's going to be mostly what I focus on today. As we get each new year of operations under our belt, we certainly are learning a lot. And as Kat just said, this is the first year we've actually migrated our seasonal water supply forecasting system from Colorado to California. So that's what we'll be going over today, is mostly the operational results from 2022 in both of these regions. Certainly want to acknowledge the rest of our little crew that's been working on this here for the last couple of years here at NCAR. Of course, there's a set of broader acknowledgements and external partners to acknowledge there. But you'll see at the bottom of this slide then the outline for today. I'm going to try and move as fast as I can through the description of the model, the analysis and forecast methods, but I certainly want to lay that out because as we've seen already, a lot of what happens in terms of assessing the impact of ASO data greatly depends on what is done with it. And so I think it's important for folks to know the kind of model we're using, how it might differ from models like SNO 17, and also what our assimilation method is and what the forecast method is. I'll then show as many selected forecast examples as I've got time for, and I'll keep an eye on that because these are like sort of mini little deep dives into individual basins. But then I'll back out and try and provide a bit more of a summary and conclusions at the end from sort of the overall lessons learned. And given we're doing 2 states with lots of different assimilations in each state, domain, well, almost 4 for each basin, 4 or 5 for each basin in California, 2 for 6 or 7 different regions in Colorado. I certainly don't have time to dive into everything, but we continue to work on that. Okay. Again, this project that we're working on with ASO here has been part of a longer term effort that Eric Skye had mentioned yesterday, as well as Craig Cotton, that we've been working on originally with the state of Colorado to look at different ways to improve forecasts of seasonal water supply, be it through different types of measurements or different types of modeling systems and modeling approaches as well. So just sort of keep hammering on a research front of sorts. I've highlighted in bold here the main things that we're going to really talk about today, which is the assimilation of the airborne LiDAR, trying to do comparisons against open loop forecasts where we have them, and then really the expansion to California for this prior year. The model we're using is the Community Wharf Hydro modeling system in the lexicon of hydrologic models. It's what you would call a physics or process-based, spatially distributed hydrologic model. It has explicit routing processes that are occurring across a finely resolved landscape. It has fully active thermodynamics with mass and energy balance closure constraints associated with them. And it has essentially multiple grids, if you will, operating at the same time. So it's a multi-spatial framework that we're using. To put a finer point on that, what we consider to be sort of the key column physics that regulate all the thermodynamics is happening on a 1 kilometer grid. So we're processing all of our meteorological data down to a 1 kilometer grid. And within the model, there's an exchange with this 250 meter routing grid that allows for water to be moved around the landscape, both as overland flow, channel flow, and subsurface flow. Want to pause and take a little bit deeper look here at the snow model. The discussion yesterday afternoon, I think, was absolutely fantastic, and looking at a lot of the issues that come up in doing forecasting of this type, and looking at basically the physical processes underneath that, what might be influencing them. The model we have here is the snow model component of the NOAA-MP land surface physics model. It has explicit vegetation canopy with canopy radiative transfer, with shading and geometry associated with that. There's canopy interception, melt, evaporation, sublimation, and unloading in the canopy. It's a mixed layer, or a multi-layer mixed phase snowpack. So we have liquid and water, liquid and ice in snowpack at the same time. It varies with in density, with depth, and over time as well, responding to fresh snow inputs and then environmental conditions thereafter. Again, we can retain liquid in the snowpack. There is a 2-channel snow albedo formulation, which is partitioned into the visible and near infrared parts of the spectrum. And so that is active, but I'll highlight that it's not yet fully optimized. I know there's a lot of interest, and we're moving towards using the ASO data to start to do some optimization with that. We've got a paper that's now accepted in print for doing some station-based optimization, calibration of these albedo parameters. And so we're looking forward to testing that over a broader scale soon, but that's not in this batch of forecasts. We have a frozen soil scheme in there. And then the last thing I want to highlight here, related to yesterday's discussion, there is no wind scouring or wind redistribution in this model. So it just really does operate as an independent column. And therefore, that imprint that we see between the meteorology and the final snow that ASO sees can be very different in times. And I've got some graphics that show that. The forecast process, I've gone over in the past, and I don't want to go into a super deep detail here. You can just kind of follow the steps of the workflow on the right-hand side. We're essentially downscaling and bias correcting our meteorological data sets. There's a couple of different sources for those that we use, whether or not we're in Colorado or California. The model has been put through a layer of calibration with these data sets, and then parameters are regionalized away from calibrated basins. And we develop some long-term retrospective runs. The red arrow there you see is the key aspect, and I've got another slide which illustrates the actual assimilation process into ASO. And then the bottom part is just sort of the production of operational ensemble forecasts from a continuously cycling analysis system. And those ensembles are generated using historical resamplings of meteorological data, much in the same way that the river forecast centers would be doing that. Okay, so this is our direct insertion process. You can see the top row here is basically what we've got in operations now. The bottom row is some ensemble DA work that we've also been doing. But the direct insertion process basically has us starting with the 50-meter SWE in depth product. We upscale that to 1 kilometer, essentially through just upscale averaging to get to our 1 kilometer model grid. And then we basically take the analysis of snowpack and blend it in with the background analysis of the model, directly overriding the SWE and depth values in the ASO survey areas. And then we run a short integration of the model to allow the model to come to a new equilibrium to those data layers. And then we take that new updated snowpack and reinsert it into the full cycling analysis system. So now it's ready to go for forecasts. There's some pros and cons to this method. It's simple, it's fast, it's computationally lean in terms of its the type of computing system you need to do that. And probably most importantly, it preserves the ASO survey values at the locations where we have survey points. The cons can be that this direct insertion can result in a model that's not really fully equilibrated, particularly with respect to maybe some large temperature lapse rates within the snowpack and some of the density variations that might follow along with that. We can also have large mass discontinuities across the assimilation interface. take a large snowpack, put it into the model where it didn't have that. Obviously, you're adding a lot of mass to the model. That might be okay. There may be situations where if you were melting out snow too early, you may actually be sort of compounding a positive runoff bias in the model. So these are just acknowledgements of the issues that come up with direct insertion. Okay, so now I'm going to move into some of the examples. These are the basins that were used in 2022 for the real-time forecasting activities. These have been covered extensively through all the briefings that we've heard from the CHASM folks and from the ASO team about what was done over this last year. And so we were running over the entire domain. You can see in the upper right-hand corner a map of the model-derived soil moisture state, which gives you the actual boundaries of the model domain. And then sort of the catchment boundaries therein are just where the ASO surveys were occurring. There's a couple of extra ones here that weren't done this year, but we've kind of loaded those either because they were done in a prior year or they were being scoped for future work. California, similar story. We've got a model domain which covers the entire Sierra Nevada here. And so we were cycling the model over this entire region. But the ASO simulations that we were handling this year in terms of the WRF hydro forecasting were only in the Feather and the San Joaquin Basin. So those will be the results that we look at today. A number of other products can be derived out of the system versus what I'm showing. Just keep in mind, again, we've got spatially distributed SWE and snow depth and soil moisture, runoff processes, a fully derived channel network, so we can extract flow at different points. There are reservoirs in the model, but they are very crudely represented, let's put it that way. There's literally no water management per se. It's just kind of a fill and spill type of parameterization for reservoirs. And that can certainly have an impact in the areas downstream of there. But really in this project, we're most interested in looking at the inflows to these reservoirs. Okay, try and get through a few different examples here. Looking at the Feather River, what you see in the middle panel there is the SWE plot across the year. The differences in the colors you see there, yellow is from the NLDAS product, blue is from our open loop model, and the green, which starts to depart from the blue partway through the season, is when we start assimilating ASO into the model. Over on the left-hand side, you can see the percentage change in the SWE increment across the assimilation interface. And so for this basin, you can see on the order about 10 to 20-ish% of change in snowpack can happen. But probably the more important thing to note here is that the larger magnitude changes are certainly coming in this particular basin here earlier in the year, and particularly with that first assimilation. That's where we're sort of wrapping up all of the uncertainties up to that point associated with forcings and other melt-out dynamics. And so while you can get big percentage changes later in the year as the snowpack dwindles, you can kind of get an artificial perception of that. Model soil moisture was also tracked throughout the year. You can see basin integrated soil moisture at the bottom. And of course, being California in this historic drought period, I've pulled some snapshots of the modeled soil moisture going from October 1st of 2021 in the upper left to September 1st, just about a week and a half ago. In the lower right, of course, you can see the dramatic wet up and then, of course, really significant dry down back again to these extremely dry conditions in the basin. And so that deficit obviously needs to be replenished and satisfied before runoff really takes significant place in a lot of these areas. So the forecast points for the Feather River system, we've got Lake Almanar here. What you're looking at on the left-hand side is a set of flow accumulation plots. This is going through the entire season of forecast going back into February here all the way through the end of October. And we're just tracking this to see how the model's doing throughout these various seasons. There are a number of different forecast dates here. I've got the actual April through July 50% values listed there on the right-hand side, and then sort of an average change with that comes from the ASO forecast, which in this case, at this particular reservoir inflow point, ASO forecast tended to ratchet down the forecast by about 10%. The other thing you can notice from the forecast plot on the left is just sort of the large variability in those forecast traces, which are almost all emanating from the very early forecasts in the season, when there's still a lot of uncertainty associated with how much precipitation is still going to fall in the basin. But as the season wears on, you can see the forecast plume really start to narrow down over and what has ultimately become the observed value here. Going down to Lake Oroville, just basically a similar behavior and similar magnitude of forecast adjustments as we saw further up in the watershed at this particular basin. San Joaquin River, here we see a much larger initial increment in that basin integrated sweep lot initially, almost 35% downward revision from what the open loop model version was happening. And then things stayed at a very small adjustment level thereafter. That's just the way it happened to work out this year. I would not guarantee that that's a systematic behavior that applies off all years. Looking at the water supply forecasts into the reservoirs in the San Joaquin Basin, this is the smaller basin, Lake Huntington. Again, a downward revision associated with ASO forecasts on the order of about 23%. You can see this basin, the black line tended to melt out and run off quite a bit earlier than what was forecasted in the model. I think that's pretty consistent with the very warm and dry and windy spring that we had. Looking at Lake Florence here, fairly similar behavior to what we saw at Huntington, and then all the way down to Millerton as well. Again, fairly consistent performance throughout the basin in terms of the adjustment statistics. Let me show one quick example from Colorado, and then I will head to the wrap up here. This is the East River Basin, again, just showing that SWE trace in the top, looking at the magnitudes of the ASO assimilation increment difference, where we got a plus up early in the year with the first assimilation in mid-April, and then a downward revision later in the year. You can see spatial maps of the assimilated values there in the bottom. The East River has traditionally been a pretty decent performing basin for us in the past. And this year, I think we're pretty consistent with that. This is a more typical forecast verification plot. And we do tend to overestimate stream flow in this basin earlier in the year. That was repeated again this year. But one note is that there's actually several significant ditches and takeouts of this river upstream of this location, which we don't have in the model yet. So as we get further in the season, the observations are baking into more of the forecast and things are closing up, but a fairly consistent performance from what we saw, and fairly modest adjustments with the ASO data here. The Taylor River, again, another key basin that is talked about. And ASO really has done a great job this year in keeping things on track. So far, all of the ASO estimated forecasts or assimilated forecasts that we've done have ultimately resided within about 3% of what's becoming the actual April through September value. And when I skip to the end here, you'll see that the increments from those are actually fairly significant. So ASO is doing a really good job of keeping the model on track here. Looking at the time, I am going to skip ahead to the end. So sorry, that's going to be right here with this forecast summary. So you can see a wide variation of these adjustment values with SWE increment. And there's that Taylor River one that I was talking about. Without ASO, the background model this year was really significantly underestimating snowpack in the basin. And I know this was referred to a little bit in some of the earlier talks as well. But by that second assimilation, a lot of the snow in the basin had really melted out in the model, and ASO really helped to keep that on track. And as you saw, the final result was to keep the forecast within a very close range to what's now being observed. So conclusions, California's conclusions, I think things went well for the first year. ASO generally resulted in a little bit of a lowering of the forecast compared to the open loop version of the model from around 8 to 25%. And so I think, that has turned out in terms of improvement in this case. We didn't see significant cases where we have any sort of massive degradation through the use of ASO in this. The point I made earlier, the large magnitude increases in SWE generally tend to have come in the first assimilation in later periods, they can have greater percentage changes, but it doesn't seem to be nearly as high as an amount. Precipitation uncertainties in the wintertime are certainly a significant source of the overall forecast uncertainty for those early season forecasts. Similar result in Colorado. We do tend to get larger magnitude corrections in general with those early season forecasts. As was brought up yesterday and the day before in 2022, we did have an anomalously dry and windy April and May, and likely dust deposition in those areas, which resulted in downward forecast revisions for many of our basins between April and May. Surveys, this is particularly noticeable in Taylor and Conejos and Dolores, as the season wore on and that snowpack was being depleted. The model in our case tended to overestimate some of that depletion, particularly for the Taylor River Basin. And so that's, again, another example of where the ASO data kept things more on track. We did have the heavy monsoon here in Colorado, and that certainly played with a lot of the forecasts, particularly some of the southern basins like the Conejos. Lesser degree to the Dolores, did the monsoon really take things in a different direction in terms of overall forecast skill. But up until early July, things were tracking pretty well with that. Final thing, just it's difficult to distill, again, very generalized impacts because of all the different details with respect to the meteorological data accuracy that we have, the forecast meteorology, the snowpack dynamics, and the runoff generation. Really, besides this idea that we do tend to get a larger magnitude increment with ASO assimilation earlier in the year, with that first assimilation, the overall results really do tend to be case by case for the different basins that we've looked at for the past couple of years so far. So it does speak to the need for sort of continued updates associated with ASO surveys and the meteorological conditions that are going on. So I will stop there, and if we've got time, I'll take a question or two.
Great talk. Thanks, Dave. That was really interesting. I'll open it up just for one or two questions if we have any quick ones. Otherwise, I'll go ahead.
I had a real quick one. Did you see any basins where there was no adjustment, right? Where the model didn't need any help?
I can't say we had a basin where over all assimilation periods, we saw no adjustment. Probably one of the better performing basins from a background model perspective would have been the Feather this past year, and a little bit lesser degree, the Dolores in Colorado. Why that is difficult to say, because we've only got one season's worth of data to look at that. But just from again, that magnitude of the SWE adjustment in that basin, it was a bit smaller. Again, as the year went on and the snowpack dwindled, the percentages stayed relatively significant, but the Feather had sort of the smallest magnitude adjustment of all those. Colorado basins tended to vary a lot more than the California basins. I'll add that as well.
Okay, great. We have one question from Jeff. Jeff, do you want to ask your question live? We can unmute you, or I can read it out.
I just gave him permission, so.
Okay. Yeah, so my question is that you didn't say much about the hydro part of WRF hydro. And the question is, if you have an estimate of the SWE, either the total volume or the spatial distribution, how do you actually translate that to stream flow? Because some of the work like that Eli Boardman has done, for example, is that historically there's lots of interannual variability in the ratio between the SWE volume and what actually comes out in the streams. So, partly due to things like soil moisture and groundwater flow and stuff like that. So how is that built into WRF hydro?
Yeah, so it goes back to this figure here, where the thermodynamics of snowpack and the meteorological forcing interacting with the land surface are essentially evolving the snowpack once it is assimilated into the model, or if you're not assimilating, it just accumulates in the model. And so essentially that snowpack in the model is responding to the atmospheric conditions that we're providing, incoming solar radiation, temperature, wind in an ablation sense, but not necessarily in, you know, a transport sense at all here. And so basically we've got a multi-layered snow model, which is accumulating and then melting, and that melt water will percolate through the snowpack into the ground. It will at times exceed infiltration capacity of the soils. It'll run off the landscape as indicated in this diagram here. It'll make its way down to predefined stream channels. We can get saturated flow in the model as is indicated sort of in this bottom corner of this little cutout diagram here. That can also contribute base flow into the channel network as well. So it's those combined sort of watershed processes which are happening on a spatially distributed grid, which are generating the runoff from the snow and then sort of translating into the stream channel and ultimately into a lot of the reservoir inflows that we saw.
Yeah. Okay, I guess it's still, you know, what Eli showed in his presentation last year was that there's certainly a relationship between this runoff ratio and the previous year's SWE. And so there, I guess, what is the source of information to try to deal with that problem?
Yeah, no, I think that's very relevant. In our modeling context, that would have to do how much water is being stored in this soil column, as well as within the subsurface structures, which are contributing base flow back to the channel network. And so kind of like Rosemary was talking about yesterday, these models have an inherent amount of storage within them in a soil column or in some type of groundwater parameterizations. Rosemary's being much more sophisticated than what we're using here. But the idea is somewhat similar in the sense that these subsurface reservoirs can wet up and dry down. And usually as the deeper you go, the longer the time scale you have that's influencing that. And so you'll get carryover responses year over year as to how much water is being stored in one of these base flow components of the model or in some of these deeper soil moisture components of the model. And that was part of what this slide was intending to show. With this is now just on a seasonal cycle, where for the Feather River, we see this wet up and then ultimate dry down. But as you see it wetting up, you can actually see the imprint of, you know, topographic depressions and terrain features as the moisture is sort of wetting up and preferentially accumulating in these downward locations, and then ultimately it drains out. And then you get to the extremely dry periods of the year, and much more of the dryness of the landscape it's a little more uniform in many ways, and it's much more dictated by other things like either vegetation or soil types and things like that, in addition to some of the landscape positions. So that storage is in there, and it's carrying over information from year to year as this model cycles year over year. So it does have a continuous cycle in that regard.
Thank you.
Mm-hmm.
Yeah, that's great. So the model has a memory of what happened, you know, previously. I have one more question from Gus, but Dave, would you be able to answer that in the Q&A for us while we truck on?
Yeah, that's for all the forecasts since mid-April, Gus, but I can certainly add more to that.
Thank you. Okay, next up we have Cody Moser and Mike Imgarten from the River Forecast Centers. So we have the CVRFC and the CNRFC respectively, and they're going to do a combined talk about the work that they've been doing. And we've been trying to step up our communications and our working with the RFCs. And so I'm really excited to see this combined talk here today.
Thanks, Kat.
Yeah.
Are you able to see my screen now?
Yes, we are.
Okay, thanks. And just wanted to thank the ASO team for the opportunity to share some of our work we've been doing with their ASO data. I'm Cody. I'm at the CBRFC, and as Kat mentioned, this will be a joint presentation. Myself and Micah at CNRFC to talk about some of our analysis we've been doing with ASO data over the last couple of years. First, quickly chat about some analysis we did in the Gunnison River Basin just to get a better sense of some of the sources of the uncertainty that go into an April 1st water supply forecast. And then we're gonna jump right into talk about how we're incorporating ASO data into some experimental forecasts that we've been working on and provide some examples and results. And then talk about some considerations when it comes to analysis we've been doing in terms of just keeping tabs on what's been changing over the years and make sure we're staying on the right track with some of this analysis. Talk about some future work we've been doing as well, and then take some questions at the end. So first, looking at, this is an analysis we did in the Gunnison River Basin, and this is looking at errors and uncertainties associated with an April 1st water supply forecast. So the graph on the right there, this is showing 4 water supply forecasts, point locations in the Gunnison River Basin. So the magnitude of the bar here, the blue plus the orange, this would be the total error for each location for an April 1st water supply forecast. And then it's broken out into 2 different sources of uncertainty. So the orange bars represent the error associated with unknown spring weather. This is mostly precipitation, although temperature also going to have an impact on what flows are seen. And then the blue section of the bars, this basically, so you can see pretty clearly about half the volume error in an April 1st water supply forecast is due to spring weather. And the other half breaks down into model error. So this would be errors in the model soil moisture, model snowpack, the parameterization of the model, and then the model structure, any assumptions that are made. So just taking a look at this first bar here. So an April 1st water supply forecast, this is Taylor Park. About on average about a 15% error, and this is looking at our model reforecast and model calibration data sets here. So about a 15% error generally on April 1st water supply forecast. About half of that due to future weather that hasn't occurred, with the other half being soil moisture, snowpack, model parameterization. So I thought it'd be useful to provide a little background. It's pretty consistent. You can see as you move around the Gunnison River Basin. Blue Mesa here, obviously a larger forecast, a little more downstream, so a little bit higher error there, but pretty consistent when it comes to about half the volume being from unknown spring weather, with the other half being model errors, such as a snowpack. So now into how we're using ASO data in experimental forecast, graphics, and products that we've been working on. So quickly, how we're using this data. So we download it, we use a GIS procedure to compute a mean aerial SWE value from ASO data, and we do this for each catchment in our model. And then on the day of the flight, we basically make a copy of our model configuration, and we use this. We do this because it allows us to do development work in an offline sense. It doesn't have any impact on our operational model states, as we do run a model every day. And then we use a direct insertion. I think this has been mentioned a few times, where we basically replace our operational snow model SWE, this would be snow 17, with the ASO estimated SWE, again, for each catchment in our model. And then we push this ASO estimated SWE states through our ESP ensemble streamflow prediction model. And here we assume the future weather is equal to average climatology. And we get an output of 30 flow traces. And then lastly, we plot the data. This would be data from our daily model runs, our official water supply forecast, as well as the experimental water supply forecast. It would use ASO estimated SWE on the date of the flight. And it is ideal to have the observed volume up to the date of the flight. It's not always the case, given gauge ice effects that occur out there, or late arriving diversion data especially. So in those cases, we need to estimate any missing data. All right, so here we're looking at an experimental forecast example using ASO data. This is for Granby Reservoir. This is basically at the very top of the headwaters of the Colorado River Basin along the Continental Divide. I'm going to start by going over this graphic on the bottom right here. I know at least one of these were shown yesterday, but just to give you a sense of how to read these, we've shown a handful of these. So what this is showing is back in middle December is when we usually start posting our ESP model guidance. And again, we run the model every day and tack on a data point to the end throughout the season. So the solid black line here, this would be the volume associated. We call it the ESP 50, the most probable forecast. So no surprise that we see this big increase as we had that huge December into early January, and then we dried out January, February, kind of steadied out here in March, and then we see some bumps up here due to kind of the monsoonal precipitation throughout the season. So our official water supply forecast we issue at the beginning of each month. That would be these pinkish, purplish, we'll call them magenta dots and lines here. So you can see typically we go with ESP model guidance. Sometimes we nudge one way or the other if we have a high certainty in future weather. So, you know, if we're sitting here February 1st, we were pretty confident that we were going to see a couple weeks of dry period. So that's why this most probable dot here is a little bit lower than our guidance, and then you can see how that evolves over time. So what is added here, this looks pretty similar to our water supply evolution plots on the web, we call them, but what we've added here is what we call experimental forecast, and this is where we're directly inserting the ASO SWE data into our model, running ESP, and then spitting out, you know, those 30-year flow traces. So the focus on these plots, I think, should be how these bluish cyan lines compare with our official forecast to some extent, but mostly on the day of our ESP model run. How are they comparing to our operational model snow states? So this graphic here, this would be an end of season graphic where, you know, we have an April through July observation here. This is shown in the horizontal dash line. So you can follow that across to each forecast that was made throughout the season and see how it verifies. And we typically forecast an April through July period. So that's what these graphics will be showing. And then the graphic finally here on the left, this would be the experimental forecast product that we put together in the middle of the season. So this would be a few days after that ASO flight here. So this blue line here corresponds to this first flight here. And then we got a second flight in this basin, which is shown here. And then we provide a table at the bottom here to compare our daily model run for that day versus the experimental forecast. So in this case, there was a flight on April 18th. The experimental forecast, most probable volume, 167,000 acre feet. And then our operational model guidance, 190,000 acre feet. So in this case, ASO SWE for that first flight was less than the SWE in our model. And then the second flight, it looks like it was very similar, basically right on top of our model. All right, so moving on, I'm going to just show a bunch of examples here. Kind of gets to the case-by-case basis that Dave Gochis mentioned earlier. It's each basin's a little bit different, and that's kind of what we're seeing too. So starting up here, this is looking at Dillon Reservoir. This is along the Continental Divide, the Blue River system. So you can see again, wet, dry out, kind of steadies out, some late season precipitation. So here, in this case, two ASO flights, and in both cases, they lined up pretty much identical with the SWE that we had in our model. So we were feeling pretty good about our snow states this season. However, the observations came in about 10 to 12% lower than what we were forecasting. So basically, RFC SWE and ASO SWE was pretty much identical, but forecasts, the observations came in lower. And looking at the same basin in the upper right here for 2021, again, two ASO flights here. And these graphics on the right are from last year, so they don't have quite all of the lines of our latest and greatest. We're not showing the final seasonal observed value here, but you can see that for both ASO flights, ASO was suggesting lower SWE than what we had in our model. So this year, basically identical to our model. Last year was lower than our model. And then looking at the bottom left, this is in the Dolores River Basin for this past season. So two ASO flights again. In both cases, ASO SWE was a little bit higher than what we had in our model. And you can see how the observations came in there. And then 2021 in the Dolores Basin, it's pretty similar story to what happened at Dillon this year. Both ASO flights, basically SWE came in right where our model was on the day of those flights. And four more examples here. Upper left, this is for the Gunnison River water supply forecast point, the east at Almont. In this case, both ASO flights suggesting lower SWE than what we had in our model. And then you can see how the observations came in there. Moving to the upper right, this is Willow Creek. This basin was 70% burned back in October 2020. So in this case, first ASO flight SWE was a little bit lower than our model, and the second flight was a little bit higher, pretty close to our model. And then what the actual runoff did here this past season was just absolutely impressive with some of the runoff rates we were seeing due to the post-fire runoff characteristics. So most forecasts were too low and we're not able to accurately capture some of those post-fire impacts on runoff. So moving down to the lower left, upper green. So there was one ASO flight here. I think this was the latest ASO flight this past season. This is the green at Warren Bridge. You can see the ASO SWE basically right on top of our model SWE there, which looks like it was pretty close to what actually came in come the end of July. And then finally, the bottom right is an example from the San Juan Basin from last year. Animus Durango, I believe this is. 2 flights, first flight ASO SWE being lower than our model, and the second flight closer, still looks a little bit lower. And then, as with kind of all of these past 2 seasons, you get that late season monsoonal precipitation kind of pushing things a little bit higher. That's all I had. I'm going to pass it on to Mike at CNRFC next.
Hey, thanks a lot, Cody. Can you guys hear me okay?
Yes.
All right, awesome.
Yes.
So thanks for Cody for going through all that and describing our methodology and everything. Our methodology here at the CNRC is largely the same as CBRFC, especially as it pertains to getting the ASO data into the model. One thing I will point out, though, just so there's no confusion, Cody mentioned in his presentation that they use ESP, which is a climatology for their forecast. Here at the RFC, traditionally we've used 14 days of weather forecast in our ensemble models. And then starting, I believe it was about mid-April of this year, we've been using 28 days of forecast in our models, and then appending climatology at the end of that. So doesn't really have a big effect. It doesn't have any effect though when comparing ASO data to the RFC forecast, because they're still they're using the exact same forecast. It's just a different starting point for the SWE amount in the model. So here I've got one of our similar plot that Cody has showed for the for some of the Colorado basins. This is for the San Joaquin at Friant. So we're pretty new to using the ASO data here at the CNRFC. This is one of about 4 basins where we've used this direct insertion method to try and model the runoff with ASO data. For those of you who are around on day 1, you heard a talk from Scott Fenema, formerly from the Bureau of Reclamation, now with the Water Master's Office in the Truckee Basin. And so he gave some results for the Truckee River, Tahoe, and for the Carson River. And so the other area that we've been looking at and doing this direct insertion with ASO data is the San Joaquin at Friant. So this is on the southern end of the Sierra. And so what I have here is our traditional trend plot that is shown here. Superimposed on top of that is a box and whiskers plot of the ASO data and the results from inserting that into our Snow 17 model. So as Cody kind of described, I think everybody's probably pretty familiar with these plots by now, but we'll kind of focus in maybe on some of the different probabilities and kind of how those change throughout the year. So we can see that on the April 1st here, the ASO data came in quite a bit lower than what our models were suggesting for the snowpack. So not only was the, you can see that the 50% is quite a bit lower. That's the dark dash line, is quite a bit lower than the dark blue line, which is the 50% for the RFC forecast. And then as we move through in time with the second ASO flight closer to May 1st, we can see that there's quite a bit of jump with the ASO forecast, but not so much with the RFC forecast. The RFC forecast as well as the ASO forecast, you can see that the kind of the range of possibilities has kind of squeezed and narrowed with the 10 and the 90s. But largely the 50% kind of stayed pretty flat, dropped just a little bit. We'll go on to the next slide, and so we'll kind of look at this in a little bit more detail of why that is. So there's always this question of how do you go about verifying ensemble forecast? I know I've spoken with many users many times, and I'm guilty of this myself. Of sometimes you just look at that 50% forecast and you're always expecting that 50% forecast to verify or be very close. But when we have extreme years like we did this year, that's not going to be the case. And this year, much like last year, we expected the forecast to verify much more in the lower end due to the dry spring that we had. So I've kind of put some numbers to the San Joaquin Basin using the 5-station precipitation indices from the Department of Water Resources. I did not include the basin is located in the southern end of kind of where the 5-station precip indice gauges are located. But I did not include the 6-station, but it kind of shows largely the same thing where you see near record or record dry precipitation for the April through June period. So looking at these totals, so you can see the April through June was about 2.3 inches basin wide, which is on the lower end about a 10th percentile. And the May through June precipitation was about 0.1, which was tied for the record driest. And I know we tend to focus a lot on the precipitation and how that played out, but temperatures also play a role in this too. Much like a lot of the past years, we had a warmer than average spring. And particularly this year, that had a big impact in that we started seeing melt even in some of the higher elevations early in March, and especially once we got towards the last week of March. So we started seeing our water supply forecast drop for the AJ period, even though there wasn't a whole lot of change in the weather forecast. It was mainly due to the snow melting before we actually got into the AJ period. So that's always something to keep in mind if we, as you start to look at those numbers, as we start to come into the April 1st period, that, you get in these warm periods that oftentimes, or sometimes it may be due to actually just losing volume before we actually get to that April 1st period. So next slide, please. So this slide here is just really a tabulated value of the first slide that I showed. And so now that we know from the previous slide, we know what those kind of how the precip fell during the April through June period, which is our main runoff period this year. We can kind of start to look at some of the verification on that. So on the far left here, I have the ASO results that are from the direct application. So the top left is the April forecast, the bottom left is the May 1st forecast. And then on the right, I have the RSC forecast. So the top right is April 1st, bottom right is May 1st. And so thinking back to those precip values that I showed, based on the April precip, we should have been around the 90% forecast, and the May through June precipitation should have been around basically our minimum, since we tied a record dry spring for that period. So using the ASO data, we see that the 90% for the April 1st forecast, we were about 150,000 acre feet too low. And for the May 1st, although we did come up quite a bit and got much closer, we were still about 45,000 acre feet too low using that minimum trace had we used direct insertion from the ASO data. If we look over on the right and we look at the RSC forecast, we see quite a bit better results here. So using the 90% verification, we were about 15,000 acre feet too high. And then if we jump down to May 1st, it just so happened on that day for that particular run, we were right at about the minimum, which we would expect, again, because of the way the precipitation amounts that fell during that period. So verification was very good there for us this year, but not as good for direct insertion of the ASO data. All right, go to the next slide, please. And so, what can we really say about that, and what does this mean? And I think that we can pretty confidently say that the direct insertion of the ASO data into the RSC model was not an improvement for this basin for this year. So that doesn't say anything about other basins, or it doesn't say anything about other years. Perhaps in other years, this is better. We saw just in this example how much better the forecast was in May than it was in April. So in future years, as we continue to learn and start using more and more ASO data across more and more basins, I think we'll start to really dive into potentially some of these biases, potentially with maybe it's the ASO data, potentially with our model, and trying to better unpack why and explain why we're seeing these differences, and why, you know, direct insertion, you know, may work well in some basins, like was shown in Monday's presentation, but didn't necessarily work as well this year for this basin. So traditionally what we have done is we've compared for the last several years to the information, the snowpacks estimations coming out of from the Colorado JPL group, some results from the ice snowbow model, results from no risk, or as we like to refer to it, the no horsey estimates. And so in the future, and as the next few years, especially as ASO is expanding into other basins, we hope to do more of this direct insertion and more of this modeling, rather than just kind of comparing snow volumes as we've done in previous years, so that we can kind of physically see how big of a difference that makes. And again, start to kind of unpack some of these biases, and hopefully at some point get to a point where we can use we can directly use that data and understand a little bit better how to use that in our models and make better forecasts going forward. Next slide. I'll kick it back over to Cody for this.
Yep. So this one here, you know, just kind of breaking it down by scenario. It's kind of covered in all cases, you know, whether ASO suite is higher, lower, similar. We've seen both better and worse verification. So yeah, a lot for us to dig into, I think, still. And then wrapping up quickly here, I kind of mentioned this before, but just staying aware of some of the implications for whether we're recalibrating our model, you know, what ESP period are we using that changed for us last year, this year, as we transition to the new 30-year normal period. You know, if we add basins, change parameters, is there any, you know, QA, QC processing changes being done on the ASO side of things? If so, is it getting reprocessed? You know, keeping in mind, we're directly inserting a high resolution ASO suite data set into lumped hydrologic model of ours, and just keeping in mind all the uncertainties. I'm not going to go through them all. And also remembering about half of the error in an April 1st water supply forecast is due to unknown future weather. You know, and there's obviously advancements happening with getting more accurate longer term weather forecasts. So this could allow for, say, more confident ESP trace selection optimization at the time of the forecast. I think we're kind of running low on time, but just quickly go through this. So we have developed a framework for producing an experimental water supply forecast using an alternative suite data set, looking to better understand some of the inconclusive results that we've seen, continuing to evaluate ASO data, bringing it into our model calibration system. It's going to be more flights over more basins, which will give us a bigger sample size, working on some finer scale modeling. I'm going to end there and open it up for questions.
Great. Thank you. Thank you so much for that talk. It's really good to see all of the experimental forecasting going on. We have a couple of questions, but I think, Tom, did you want to?
Yeah, I want to, let me just, let me bring in the scatter plots from the poster, and then just speak to the details of this, because I think it's really important to speak to this right now. Can you guys hear me okay? I see my head on your computer. it's moving herky jerky.
We can hear you and see your head.
Okay. All right, great. All right, so so this is just a few years of comparisons of zonal snow water equivalent, snow 17 versus ASO, and so in the case of a model like snow 17 versus a physically based energy balance explicit model. In the former, there's an enormous amount of calibration, and one of the questions that's really important to ask before we do this, and I can say that there was anxiety in the very beginning years ago when we were talking about, okay, how do we handle direct insertion into Snow 17 and into other calibrated models? The question really is, first of all, the ASO retrieval is quite accurate. So representing the actual snowpack that's out there. And so then going about directly inserting that into the model only makes sense if what the model averaged over time is simulating for a snowpack is one that is close to the reality. So in other words, if overall a regression between these two results in a slope that is close to 1, and otherwise you're directly inserting something that the model is not wanting. And so if you look over here on the right, for instance, in the Tuolumne Basin, you can see this substantial bias between the two. Likewise, in Cherry and Eleanor, when you combine all of these into what's the Tuolumne Extendo, which is the combination of those two, well, it ends up ballpark right. But for the sub-basin case, that's not valid. So I think it's really important to keep locks on. ASO is a very accurate measurement of snow depth, and with the assimilation of the snow density and an understanding of its uncertainties, which have been updated likewise to be unbiased, then that snow water equivalent retrieval for the basin is highly accurate. So it's really important to start doing these analyses through time, and it's something that we talked about with Patrick Kormos a couple of weeks ago in going back through some of his slides. So I think we need to be really careful about not saying ASO doesn't help here. More so, we need to look at it in terms of, okay, this accurate measurement does not fit well with this model, but it's just the language there has to be really handled carefully to understand our path forward. And so one of the things that we talked about with Pat a couple of weeks ago was continuing to put together these relationships to determine what is per basin, what is the model actually trying to get at as a snowpack? Is it 50% off? Is it spot on? And so I'll leave it at that. And of course we can carry that on in discussion this afternoon. And then Dave Gochis, you had a question as well.
Yeah, I think it's a quick one. I don't know if it's a single answer or if it's a it depends answer, but it's to Mike and and Cody there. The question is in the official RFC forecasts for these downstream reservoirs, the big ones like Oroville, Granby, Blue Mesa, so on and so forth, are the upstream diversions out of the system, or transfers into the system for that matter, are they explicitly accounted for as sort of an adding and subtracting of the flows, or are they just sort of implicitly accounted for through calibration, or does it just kind of vary depending on the basin and the sort of the size of the management activity being done?
Yeah, I can go first on that, Dave. Yes, we explicitly account for diversions in our calibration and in our forecast. So ultimately, what we're after in every reservoir is really the full natural flow, the F and F. Whether that's, so we do account for anything coming in or going out of the basin. Certainly, there's areas where there's very small diversions that may be taking place that aren't accounted for, but anything that's sizable, we do directly account for it.
Great.
Yeah, that's the case at CBRFC as well. So we're calibrating to an unregulated flow time series.
Okay, so in that sense, Cody, you're kind of adding diversions back into the flow time series, and then you're calibrating the model to that sort of naturalized flow.
Correct.
Okay, cool. Great, thanks a lot.
Okay, great. We're running low on time, so I think I'm going to skip ahead to the break, but I do want to point out that we have a couple of open Q&As from this presentation. So Cody and Mike, if you would be able to go and take a look at those and perhaps respond if you can, that would be super useful. We can also continue this discussion, which I think is really important discussion. We can continue this in the section later this afternoon if folks want to return for that. So let's take a 5-minute break. We'll get a coffee, and we'll come back at whatever that is, 11:12 Pacific. We'll come back and we'll jump into some more modeling work from M3 Works. Let's kick this off. We have the next round of talks. We've got 2 talks. The first one is from the 2 Micahs, Micah Sandusky and Micah Johnson from M3 Works. And they're going to be talking about some improvements that they've been doing to their implementation of iSnowball, particularly with the soil temperature. But I want to preface this by saying that this is just one of the improvements that M3 Works have been doing over the past year or 2 years, really. And the improvements of their implementation, really add to the physics of the iSnowball model that they have running for us. And so this is the next step in something that's been going on for a long time. So Micah, take it away.
And to add to that, Mark Robertson's part of our group that's making these changes too.
Yes, he's the third M.
All right, I'm gonna try to share my screen. Can you see it?
All good.
Great. Okay, so my name's Micah Johnson, and I'm one of the 3 M's in M3 Works, and we provide the baseline density product for ASO's suite product. And we run a model called iSnowball in real time for all of the basins where we do modeling for them. You'll have to excuse me, I'm just getting over a cold, so my voice is a little hoarse. If you were in on any of the conversations we had this year about the model performance and how flights were adjusting the model, a lot of the times we were talking about things like precip, and soil temperature came up a lot. And Chad Moore mentioned this yesterday, that he didn't think that the over adjustment in the models was just from precip alone. He thought that there were other things buried in there. And we agreed with that sentiment. And that's why we started looking closely at soil temperature. Now, for those who don't know, what we do is when we're running the model, we run it just in its natural, or I guess normal design state. And then when ASO flies, we get a flight and we bring that into the model and update the model and then go from there. And we often use that as a metric for determining what's happening in the model. And that's what prompts a lot of these conversations about what can be done to make the model better. So here's some of the reasons that led us to think soil temp was the issue. So for one, it's probably the most crude piece of ice snowball, as it uses a constant temperature of -2.5 C. That's the default value. You can change that, but it is just a constant swath of the temperature that we're using for the soil that's going to lead to, how the snow is being affected by the ground. So that right there makes it a pretty good candidate that something's probably not right. And we know that the soil temperature does vary across the basin. So we picked that at the very beginning because we thought this is a really crude part of the model. The second thing that we saw in, I think, every first flight and then most of the subsequent flight updates afterwards is that the model snow-covered area was being reduced, which says something about the lower elevation snow that we see in the model. Along with that is that a lot of our lower elevation basins needed more adjustment than, say, our higher elevation basins. And again, this is kind of funneling us all back to this thought that maybe the ground temperature isn't right. And the final thing here was, and we saw this in not just California, but we saw this in Colorado also, was that in some of our sparsely forested areas, we saw the model hanging on the snow a little too long. And to us, that suggested that maybe in areas with limited radiation getting through the canopy, there was some energy budget mess up. And so again, we're going back to soil temperature there. So these things kind of all funneled us into this idea that soil temperature might be contributing a significant portion to the model that in the past we've thought has not been really that big of a thing to check on. So the first and quickest, easiest check on that is to see what some of the soil temperature stations are showing. So here's just an example of a few years at Dana Meadows there near Tuolumne. And you can see here during the typical snow cover that the temperature hovers kind of around 32 degrees. So right away we can see that ice snowball in its current state was holding snow colder than probably what we're seeing in reality. And this is something we saw at pretty much all stations that we could find with soil temperature, and not just in California, but also in Colorado. Yeah. So we had this question earlier in the year as we had these conversations with all the stakeholders about why does the soil temperature matter? And so I thought it was important to show kind of this diagram of how ice snowball is formulated. So it's a 2-layer energy balance model. It's physically based. And there's all these fluxes that we're accounting for on the surface. And then there's the ground flux going into the bottom layer, and then the interactions in between. And when you see, just even looking at this diagram, if I asked you what surface of the snowpack to look at and be concerned about, we'd all agree that the surface has a lot going on, and therefore we should spend a lot of our time tuning and trying to get our calibration set based off of what's happening at the surface. And we're not going to say today that the soil flux matters more than those things, but it's pointing out that we have a lot of parameters for messing with the radiation inside the model. And we spend, I'll say 90% of our time tuning those knobs to try to get a better result, while all the while ignoring this constant conductive heat flux in the bottom of the snowpack. And so the question really is how much energy does the soil provide to the snowpack, and does it really matter? Because we've heard in the past, even in our early ARS days, that it's kind of this second order thing in the background that we don't care much about. So what we can do now is ice snowball outputs all its energy fluxes. And so these are just summarized energy fluxes for the Merced. And this was for our ops run last year, or 2022. And in gold mustard colored here, you can see our net radiation flux. And then in brown, you can see our soil flux. And in the background, you can see the SWE time series. So hopefully that gives you some sense for how much snow is going on. And keep in mind that energy going into the snowpack is positive and energy coming out is negative. So energy in means we're warming, energy out means we're cooling down. And for the most part, the soil temperature is not changing a whole lot there because we use a constant number. And we see the net radiation flux changing. But what I was curious about is what proportion of maybe the total energy exchange, if we were to say absolute value of all the energy exchange going on in the snowpack, where does soil temperature contribute? And I think what surprised me was that in the early season and even some in the mid-season, it's it's a significant portion. And on average, it's about 7% of the energy budget, which to me right away said, this is not something we can really ignore. You know, maybe if it was 1%, we might've been able to say, we'll deal with it in 5 years or whatever. So that kind of expedited it a little bit. So what we did is we took the Merced and we implemented a distributed soil temperature that we took right from her. And we reran last year for the Merced. And the reason we did that was that we typically use the Tuolumne because it has this huge data set, but the Tuolumne is kind of high. And so we really wanted to have a basin that had good relief, some lower elevation snow that we could focus on. We've been doing it now for a while with the Merced, and it's close to some of those soil temperature measurements. So, the soil temperature measurements. So we know that by messing with this, we have something we can kind of check on along the way. One of the first things we were really curious about was what kind of variability would we see in the basin? Maybe after our first run, we'd see there wasn't much variability, and so a constant number does make sense. But pretty quickly, we could see that there's a lot of variability coming from the Her product into there, and we think that's a really good thing, especially when you look at just the couple of snapshots here. This is a GIF showing how this temperature is changing in pretty short time periods. I think the thing that we've all observed when a snowstorm comes through and it just kind of leaves a dusting, that usually by the end of the day, it's melted off. And so for the model, when we hold the ground temperature at negative 2.5 and a dusting comes in like that, we often wouldn't melt it out. And we've seen that in stations where the station would melt out pretty quickly and the model would just continue to rise. And you can see here where if we had a no snow situation on those lower elevation parts in the red and snow came in and dusted those spots, we would melt it off pretty fast now with this new temperature. Whereas before we basically put it on an ice box and say, hang on to it forever. So we saw this as a good sign. Now here's just the summary of the SWE for the ops run. That's the run we ran this year for ASO, and then the new run with the distributed soil temperature. And we've got highlighted on here all the flights and how the flights adjusted the model. I think the really promising thing to us was that the first flight had a huge reduction in the ops run. And now with the soil temperature, we see a pretty good reduction of the reduction. And so now we're closer to what the ASO values came in at. But really importantly, and I think this is a question probably everybody has that uses this data, is how is this going to mess with our data sets downstream? And one of the things that happened here on the, if you can see my mouse, on the 428 flight here, we almost nailed the data there when the flight came in. And of course, there's some redistributing stuff, but from a total volume standpoint, we had it pretty dialed there in the ops run. And you can see here with the distributed soil temperature, that doesn't change. That's a really good sign for seeing an improvement on the first flight and not messing up places where we were already doing a great job. On that last flight, you can see that we definitely go in the opposite direction. There's a little bit of more of an adjustment. And those are things that we're still exploring, but that's pretty late in the season at 5:13. But it's still something that we care about. Something that I mentioned at the beginning is that we've been monitoring the snow-covered area. So I thought it would be important to show how this changed that. In the first ops run of 2022 for Merced, we saw the snow-covered area was greatly reduced on the order of like 15%. And you can see here on the what would be some of the lower elevation stuff here, where the model had snow and ASO didn't. And now with the distributed soil temp, pretty much all of that goes away. There's a couple of places where ASO had snow that we didn't. So definitely some spaces where we need to examine what happened in those little spots. But now the change is somewhere on the order of 1%, which is great. We're really excited about this. And this is just for the first flight. We see similar results for the subsequent flights as well. And just to show the SWE change here, so this is the flight minus the day before we adjusted in the model. Here on the left is the ops run, and you can see all that snow down here in the bottom that got taken away. And now we're adding back in just a little bit from the ASO product. And again, this is the total volume number changes is really significant. It's quite an improvement. This is the kind of stuff that makes us nerdy modelers jump up and down like we've struck gold. Now, kind of a re-look at the energy budget and how it got modified from this. On the left is our ops run. You can see that it's still that flat line from the soil here in brown. But now with a distributed soil temperature, we have this kind of U shape. And if you remember the soil temperature measured at the station Dana Meadows, it does have that U shape. And we know that the snowpack really can't change much between beyond 0 and say -15 degrees. And so we kind of expect that the soil temperature contributions to the energy budget should look something like that U shape. And this is really, I mean, this isn't an exact, yes, this is an improvement, but we know qualitatively that this is what it should look like. So going from that flat line soil temperature energy contribution to this U shape tells us that we're heading in the right direction. And as an operational snow model, heading in the right direction is always a good thing for us. So we saw improvements pretty much across the board, especially in relation to the first flight when we reran the Merced. We saw improvements in the snow-covered area, improvements in the SWE change, and even in the SWE distribution. All those things have us, high-fiving all around. But it's only one basin, and that can make some folks a little nervous to run one basin and make decisions off of that. And so we're in the process of rerunning stuff. So far, we've reran the Yuba, the Wind Rivers and Blue and the Taylor, all for 2022. And the results are almost exactly the same. We see massive improvements in the snow-covered area. We see reductions in the SWE update. And the big thing here is that when we first ran this, we still had on all of our, what we call radiation band-aids. In places where we're not melting at the right rates, we put in these kind of non-physical knobs to make the model work in the right direction. And one of those is a time-based melt decay that we add on to just increase the melt after peak SWE. And that's something that, as far as I can remember, has always been used in ice snowbound. And now, for the first time ever, with distributed soil temperature, we don't need that knob anymore. In fact, we had to turn it off to make these runs work well. And anytime we get to take away non-physical band-aids or knobs in the model is a really, really good thing. It helps us be more flexible when we go to other basins because we don't have to reset those knobs to what that basin needs. And it's just we just see that as a massive, massive improvement. So as it stands right now, we think that this is going to be rolled out in Ops 2023. There's a few more things we want to check. We want to look at exact comparisons of the modeled soil temperature to those stations. That's something we're still cooking up. And we want to rerun some of our higher basins to make sure that we're not carrying a warmer temperature up the mountains. So outside of that, we just want to say thanks to ASO and DWR. We use the CDEC network a ton to do this stuff. We obviously use her from NOAA. That's a huge resource. And we use the Snowtail network from the NRCS as well. Those are all really awesome resources for what we're doing. Thanks for your time. I'm happy to answer any questions if you've got them.
Great. Thanks, Micah. That's looking really good.
We're pretty happy with it.
I don't see any questions, but I will ask one quick question.
Sure.
So changing the sort of the bottom of the snowpack, I guess you would say, the temperature there, you're changing the temperature gradient throughout the snowpack. Do you see that impacting the cold content estimates as well?
Yeah, it's definitely going to mess with the cold content just because in now these lower elevation spots, we're warming it up faster than say we were before.
Right.
But based on those snow-covered area estimates and the comparisons, I really think that that's trending towards reality, that they probably are warmer than what we were originally showing.
Yeah, I think that's great. And so that will help get the timing right as well as we go forward through the season as it's approaching ripeness or meltingness.
Right.
But not a big density effect.
Well, it's kind of an interesting thing. And this was something I theorized a little bit with Kat, especially when we were talking about the density in some of these sparsely forested tree areas. Ice snowbound has a max density of, I think, 600, and it will trend that direction as long as the snow is there. And what happened, I think, is that because we had a cold soil layer, we were holding on to soil or the snow longer than, say, reality. And so it got to compact towards that 600. And several times, Cat and company felt like we needed to adjust those densities because we weren't seeing those in the measured pits and whatnot. And so what happens when we turn that temperature up is we actually get rid of that snow before it gets to go to 600, let's say. And we actually see in some cases here, especially in, I think it was in the higher elevations, Micah and Mark can correct me on that, that we saw a lowering of the density, which is kind of counterintuitive when you think about warming it up. But I think we've increased the melt timing, and therefore we're getting rid of high density snow that would otherwise sit there and want to become glacier-like.
Right. No, that makes a lot of sense. I think I'll be really excited to dig into that before the head of next season. Okay, one quick question from Frank. It's come in. Did you compare her to measured soil temperature?
Not yet. That is part of our hesitation for saying we're going to roll this out, is we want to look at all of the spots. We have some infrastructure we had to put in place for the model to be able to extract that, because soil temperature is an input to the model. So it's not a variable that we necessarily hang on to, not like SWE that we hang on to every day. But the soil temperature is an hourly product. So it ends up being a lot of data that we typically will distill and make up a couple of statistics on it. And we put in a daily or an hourly point in a database for us. What we've started doing is extracting out the points around stations to be able to make those comparisons retrospectively without having a terabyte of data for input data sitting there. So those are still being populated, but that is the plan.
That'll be great. Lots to chew on there. Okay, that concludes our sort of operational modeling portion of today. We're going to transition into more science talks. So we have our first one now before lunch, and then we have four more after lunch, just before the discussion session. And so the next talker is Ken Williams, and he's going to be looking at different ways to incorporate ASO data into, answering some science questions with respect to water management. So Ken, I see you're sharing a screen and we can see it.
Yeah.
Okay, away you go.
Great, thanks so much. So this will be a little bit of a change of pace, and hopefully it's of interest. It's going to be much more forward-looking. Indeed, I'm actually going to share precious little airborne snow observatory data, but really I'm setting the stage for some research activities that myself and my team are looking to begin to get involved with in conjunction with both ASO Incorporated and the Colorado Airborne Snow Measurements Program. And so the title of today's talk is ASO in the Upper Gunnison Basin, but specifically looking at some future research directions in active land management for water resources. Again, my name is Ken Williams. I'm a senior scientist with the Lawrence Berkeley National Laboratory, and I'm speaking on behalf of a much larger group of researchers that form what's called the Watershed Function Scientific Focus Area, or SFA team. And so our operational domain is in the Upper Gunnison. And so on the left, you can see an image of the Upper Colorado River Basin, and highlighted in the two blue shaded areas are the Colorado River main stem, and then below it, the Gunnison Basin. I think most people know here that the Gunnison River is an incredibly important tributary system within the Upper Colorado River. Indeed, it contributes over 40% of the stream flow of the Colorado River as it exits the state of Colorado and enters Utah. So it's a really important system, and we've been working there for a number of years, actually beginning our research program in the East River, which you're looking at sort of an elevation map that sort of sets the stage for our research areas. We've been working in the East River, sort of looking at impacts of climate change and climate perturbation on the ability of mountainous systems to retain and release water. Our work started there in 2014 and has now really begun to grow into issues that are relevant to the East River, but in some ways potentially even more relevant to the Taylor River, and that's the eastern portion of the domain. And for those of you not explicitly familiar with the Upper Gunnison itself, it's actually the confluence of the East River and Taylor River in the town or the town site of Almont that forms the Gunnison. So the merger of those two rivers forms the Gunnison and Almont, and then down it heads to meet the Colorado in Grand Junction. And so what we really love about this particular model domain is that it's truly a model ecosystem for studying mountain hydroclimate, mountain hydrobiogeochemistry, in that it exhibits a large number of gradients in land cover, land usage, bedrock or geologic composition, climate, and relevant to ASO in today's talk, snowpack accumulation and retention. So this is where we're going to be working. And so I promised a little bit of ASO data here, working in partnership with the state of Colorado and the CHASM program, as well as funding from the Department of Energy, who funds all of our research in the Upper Gunnison. We flew a total of 2 snow-on flights. We've been collecting data with ASO for many, many years now in the Upper Gunnison. And so we established the snow-free data a number of years ago, I think going back as far as 2019 or thereabouts. This year, we flew the traditional peak SWE. What you're looking at here is the peak SWE flights for both the East River on the left and the Taylor River on the right that were collected on April 21st of this year. While I won't show them, we also flew kind of a later season mid-May flight to look at snowpack retention at higher elevations. And so this is sort of the traditional way that our team and other water managers have been thinking about utilization of ASO data, is really using it for snow resource mapping. What is that sort of volume of water embedded in the snowpack at a given point in time that can then be fed through predictive forecasting models that impact things such as the Taylor Park Reservoir that you see on the right-hand image of Taylor River in terms of inflow forecasting projections. Because this will come up a little bit later in the talk, I'm highlighting in red sort of a new expanded area of investigation that ASO flew for us this past year. It's referred to as the Union Park or the Lottis Creek Drainage System. And so why are we interested, or what are we looking at interested in sort of using ASO to link to active land management? Well, particularly in the Taylor River Basin, and as far as the Gunnison National Forest is concerned, the Taylor River Basin is ground zero for forest health and land management activities. And they're way out in front of this, and I'll touch on that in just a second here, but they're really looking at a broad class of activities within the Taylor Park and the extended Taylor River Basin that focus on large-scale prescribed wildfire. And prescribed wildfire, I mean, occurring at the scales that sort of Mother Nature intended, namely stand replacing scales. So thousands of acres, not just little spot burns. It's also a really important area for forest management in terms of commercial and non-commercial thinning. While the Taylor River Basin, for the most part, has withstood the impacts of insect-driven mortality, particularly mountain pine beetle, it's coming. It's actually nipping on the doorsteps of the Taylor River Basin right now. So a lot of issues with respect to forest health and management to improve and maintain forest health. And so I sort of asked this big question, can ASO data products actually provide insight into the consequences of forest management? I think we can all sort of speculate that the answer is going to be yes, but let's take a quick look at what we mean here by active land management. And so the planning and execution, the Forest Service, and in particular, the GMUG, or the Grand Mesa, Uncompahgre, and Gunnison National Forests collectively have really gotten out in front in an incredibly proactive way by performing NEPA assessments over the entirety of a huge Forest Service or National Forest block. These segregate in a couple of different action areas. We'll focus on the Taylor River Adaptive Management Plan. But what essentially the Forest Service has done has gotten out in front of all the NEPA planning requirements to permit commercial and non-commercial timber sales and prescribed wildfires. So these are happening. This is not hypothetical. This is coming. There are established timelines for when these various land management activities are going to occur and where they're going to occur. And so going back to that sort of subdomain within the Taylor, here's a perspective view from Google Earth looking at the Taylor Reservoir, but in sort of the foreground, highlighted in red, is that Lottis Creek or Union Park system. It's a particularly interesting area for us because, one, it's a defined catchment. 100% of the flow, well, the flow derived from snowmelt, flows out of a single culvert from the system. And so from a mass balance perspective for water inputs and outputs, it's like a perfect experimental domain. What I'm highlighting here in kind of the green shaded areas are the 3 large stand replacing wildfires that are proposed for the Taylor Park and Taylor River Basin. Those are roughly 5 years out, but of course, sort of annual weather conditions are going to dictate when those occur. Right now, we're looking at roughly 2028 to 2029 for these large scale planned fires. And so I want to sort of highlight with a video fly through what the scales in the relationship between forest cover, snowpack accumulation, and the river system are looking like. This is drone-based photography taken by a former intern of mine a few months ago, and you're looking at the Union Park area on the far upper right-hand side. That's the park cone. That's kind of a well-used snowtail location that folks may be familiar with. But what I want to give you a sense of the scales that we're talking about here. While we're interested in smaller plot level scales with respect to proposed prescribed wildfire, we're really looking at, sort of scales or spatial domains that we can't capture so easily with boots on the ground. And so this really lends itself from a sort of a scientific or an experimental perspective to folding in ASO data to start looking at consequences of lighting that forest we just flew over on fire. And so we can turn now in advance of those sorts of land management activities back to our snow-free LiDAR data sets derived from ASO overflights. And so these wind up being really important, and I don't know if these are utilized quite as often as they should be, but really what we're able to use, or in this case, Jeff Deems, who pulled this data together, is to use the snow-free LiDAR data sets to actually look at canopy demographics, so forest stand structure. What he's plotting here are variations in canopy height ranging from 3 to more than 10 meters within that Union Park Lattice Creek drainage, and highlighted in the yellow shaded areas, those again are those large 1,000+ acre prescribed wildfire plots. And so, of course, we can start folding in our peak suite, our late season flights for multiple years going forward. Here you're looking at snow depth derived for that same Union Park Lattice Creek drainage area. So we get a sense of what interannual variability is like for many, many years, precursory to the disturbance event from the wildfire event. So this is an absolutely perfect setup for a natural experiment. I know some people have been using ASO data to look at consequences of large-scale fire from California and elsewhere. This is potentially a controlled experiment. We're not running around chasing wildfires and capturing data after the fact. We have a chance now to be collecting and assimilating ground-based data, fixed wing-based data, such as ASO data products for multiple years prior to lighting that sucker on fire. While we won't go into this now for this particular site, I do want to highlight that within this lower region, there are ongoing and planned timber harvest sales that will be modifying stand structure in a pretty dramatic way. That will also occur within the area of investigation for our existing and planned airborne snow observatory data. And so thinking about logging, thinning, and plot scale experimentation, we have the opportunity to, we've had the opportunity to recently get involved with the ASK program, that stands for the Adaptive Silviculture for Climate Change program. This is a national program. There are actually 3 ASK study sites in the state of Colorado. The one in the Taylor Park area, it's called the Taylor Park ASK site. It is overwhelmingly dominated by lodgepole pine. And I think most of you know, particularly those that have lived or spent time on the Front Range and the mountains in that area, lodgepole pine is not some boutique tree species. On the far right-hand image highlighted in green shows the southerly to northerly extent of lodgepole pine. It is tremendously common. It's a montane tree species of the Rocky Mountain West. It typically grows between 8,000 to 10,000 feet, at least in the state of Colorado, that's the case. Likes fairly abundant precipitation, 20 to 30 inches, and it really tolerates cold temperatures and nutrient poor soils. In the state of Colorado alone, that's what you see with the map above shown in highlighted in red. We have 1.5 million acres in the state. So it's an important tree species, and it's important tree species from a management perspective because timber companies like working with it, right? Good older lodgepole stands can provide a lot of usable stud lumber. And so there's a big commercial value for it. And so one of the ASO plots in Taylor that we're getting involved with, again, you can see the Taylor Reservoir on that left-hand image, and outlined in red is the Taylor Park Adaptive Silviculture for Climate Change, or ASC study area. And so these study areas are pretty interesting. There are 4 different blocks. You can see that in the middle figure there, block 1, 2, 3, and 4, each of which has 5 treatment areas, so 20 total treatment units. Each treatment unit will be 25 to 30 acres. All of the blocks have similar aspect, elevation, hill slope, and canopy structure. 3 of the blocks are going to be manipulated, and 1 block will serve as a control. And these manipulated blocks actually are going to be designed to propose treatments that confer resistance to climate change, resilience to climate change, and transition. So effectively what's going to happen is you're going to have a large amount of clear cutting that takes place, followed by replanting and revegetation. So it's a really interesting opportunity to start looking at how abrupt and then evolved changes in forest canopy characteristics impact snow water resources. And so back to our big question here, what role can ASO serve here? Well, I think I'm telling people what almost everyone knows, and that's forest canopy and snow have an intimate relationship. Specifically, forest canopies and their canopy structure can intercept snow and help contribute to sublimation, namely not allowing throughfall to the land surface. That snow depth is frequently less under canopies, at least in evergreen canopies. Those forests and precursory or posterior stand structure is greatly going to impact wind shielding, shading, ground temperatures, snow redistribution, and of course, these temperatures that drive melt in more open areas can allow for much earlier snow melt. So that's our big question again. What role can ASO serve here? Well, the answer is that ASO in our case can and will serve as a spatial integrator for investigating natural and manipulated snow dynamics. And so here on the left is sort of the traditional view that we've been thinking, which is again, assimilating snowpack information, water equivalents, water reservoirs at multiple times during the year over scales that range up to 3,000 square kilometers. Now we're really looking at bridging and integrating those scales down to levels as small as 30 acres to look at consequences of land management, such as timber cutting, timber sales, and prescribed wildfire, to look at consequences for snowpack accumulation, retention, and ultimately water resources. And with that, I want to thank everyone and thank the programs that have both funded and supported this activity. Happy to take any questions or hopefully comments for those of you on the ASO side of the house that have worked in the space of active land management. Thanks again.
I was hunting for the mute there. Great, great talk. Really interesting work there, Ken. I'll be looking to see those results when you start coming up with the analysis. Okay, do we have any questions? I'm not seeing any, but if anyone wants to ask Ken some questions.
How do the locals feel? Because I mean, I understand the need to light the sucker off, as you said, but I got a friend who was the chief forester at Yellowstone who kind of got in trouble when during the big burn, he was on national television and said, "Burn, baby, burn,"
Yeah, it's a great question, a great comment. So the Taylor River and Taylor Park in particular has had a long history of forest management. And so it's not an instance wherein the Forest Service is parachuting into some pristine wilderness area, which of course they couldn't, but some pristine environment where such work has never been proposed or done before. So on the commercial timber sales, that's one thing. To your point about the prescribed wildfire, that definitely makes people concerned, and there's a lot of precursory forest management work that's being planned in advance of those wildfires. The public is actively engaged as a part of that Taylor River Adaptive Management Group. So we think we're building consensus, and the hope is that conditions will allow precursory forest management work will have taken place, and we will be able to burn those lodgepole forests, if you will, the way God intended.
And along those lines, is there I'm not an ecologist, but is there an ecology reason? I mean, do you need the wood there to burn to get the burn result rather than like scorch them after a clear cut?
Yeah, those are very different models for forest management. As certain foresters have told me, one model is cut it flat, burn it black, and grow it back. And so that's one model. The other model is to, again, try and operate within the normal ecological behavior of these systems, which is large-scale stand replacing wildfires in lodgepole forests that have a recurrence interval of roughly 100 years.
Yeah.
We have lodgepoles in the Taylor River Basin that are as old really as anywhere in the Western United States. We found lodgepoles there that are in excess of 300 years.
Wow.
And that really highlights the strong fire suppression activities that the Forest Service, well, that has been Forest Service mantra for many, many years. The new Forest Service models are really moving toward proactive management to really improve forest health, but then also have knock-on consequences for watershed health, particularly in terms of water resources. That's the space we're interested in getting involved with, and that's the space that I think ASO, CHASM, and other programs really have a role to play in.
That's really cool. Thank you.
Thank you.
Great. Okay, I think we'll take our lunch break now. One thing I do want to note before we break for lunch is that there are quite a few questions in the chat. Well, there's a few questions in the chat and some good, interesting discussion happening around, that was sparked on from the RFC chats that we had earlier. And I think we're going to pick that conversation back up in the discussion. So I really want to encourage folks who want to be here for that, and we'll address those questions at that time. So that's going to be after lunch and after the next session. So let's break. Oh, Jeff.
Quick note. I was going to announce this at the end of the day today after we had completed our program. But given those questions that you just mentioned and a lot of the good discussion earlier, I want to announce some candidate dates for the ASO modeling workshop that we have discussed, actually starting with this time last year, following on a bunch of similar good discussions from the ASO workshop in 2021. And a lot of the comments and questions today dive into this. So we've identified the window of October 25th through 27th as probably the best time to do this. And so I wanted to get folks to kind of block those dates out in their calendar now. We're actively developing the agenda and program for that, and we'll be reaching out to a bunch of the folks that have been engaged in the discussion today, and hopefully we'll be back for this afternoon's discussion as well. So that's my pre-lunch announcement. Go forth and eat sandwiches.
Perfect. Thanks, Jeff. Good opportunity there. Okay, so let's reconvene on schedule. We'll come back at 12:45 for a 12:50 start, which is all in Pacific time. So do your adjustments as required. Okay, see you all after lunch. Righty. Welcome back, everyone. We're going to finish up this afternoon with 4 science talks. Kicking it off, we have H.P. Marshall from Boise State University, and he's going to be addressing some really interesting questions about how can we, use remote sensing techniques to get at the snow density, which is something that ASO can't do from the plane with the instruments that we have right now. So take it away, HP.
Great, thanks, Kat. Just want to thank the ASO team for giving me the chance to chat with you today. I've been super impressed with the operational impact of ASO, and just want to say that the scientific impact has been equally as huge. We would have been very hard to fund these kind of LiDAR time series for scientific reasons. So big shout out to that group. I'm kind of coming at this from more of a radar perspective. So I'm going to talk to you a little bit about radar, but in the context of where it might fit in with ASO-like operations, and where it might be synergistic. So the radar has this path to space. It can see through clouds. We can use it at night, but interpretation has been very, very complicated. And so I'm going to talk a little bit about some of those challenges, and then why we need good maps of snow density to get our retrievals at least in the right ballpark. We need an initial guess of snow density. So the basic idea that we're using here, there's sort of 2 approaches using radar for snow depth or SWE. One is looking at the amplitude of the amount of energy that comes back to the radar receiver, and the other is to use the time of flight. So very similar to the LiDAR, we're measuring and tracking the amount of time it takes this radar signal to travel through the snowpack. And so the difference is, rather than reflecting off of the surface, in this application, we're using a low microwave radar frequency where the snowpack is essentially transparent and the wave travels right through the snowpack, hits the snow ground interface and returns. And depending on how much snow is there, that changes that time of flight coming back to the sensor because that wave slows down in the snow. We have automated algorithms for these ground-based sensors that work well in dry conditions. Wet snow causes various challenges that we're starting to overcome in some situations, especially at the lower frequencies. But the basic idea is we're measuring time of flight through the snowpack, using that to get snow depth and snow water equivalent. If we have an independent estimate of snow depth and we have that travel time, we can measure the velocity or the speed of that wave through the snow, and that allows us to estimate the density. That's the basic idea I'm going to be talking about today. So just a little bit of background. I showed some of this at the last ASO workshop, so I'm going to go through this fairly fast so I can get to the density piece. But in 2017, we had our first opportunity to fly this really low frequency type of radar that measures phase changes. So it's called an INSAR that's been used a lot for earthquake and volcano type monitoring activities. We're using it to measure this change in time of flight. The SnowX campaign in 2017 wasn't designed to measure changes. It was designed to measure the total. And this approach really measures the change between overflights. And we have to have those overflights within about 2 weeks to a month of each other. So it's hard to do a total amount, but it's a great tool for tracking changes. So on the left, I'm just showing the change over a 2-week period on Grand Mesa. 0 to 25 centimeters is the color scale there on the left. And then comparing it to ASO snow depth pattern on the right, which is 100 to 170 centimeters. So we're kind of comparing apples to oranges here, but the basic idea is that snowfall patterns tend to be relatively consistent at this site. And you can see a very similar pattern with a gradient from the west to the east, which is kind of the main direction of the wind. And you can see a lot of drifting in that northwest corner that comes through in both techniques. So in 2020, we managed to fly LiDAR right in sync with the UAV SAR. And so these are more apples to apples. Both color scales are plus and minus 25 centimeters. So you can see a lot of those patterns look very similar. We used field measurements of density in this case to estimate the wave speed. And that's what I'm going to talk about, why we need those estimates. But we're seeing, drifting and scouring at this 20 centimeter level. There's one tunable parameter, which is just defining the place where there was no change. So that's the one piece that we have to add. But when we do that, we get pretty good agreement. The histograms are on the left for the LiDAR depth change compared to the INSAR depth change. And then the scatter plot there with a root mean squared error of around 5 centimeters. So while this isn't ever going to replace LiDAR, it's not better than LiDAR, but it's something that we are going to get very soon from space, and I think can fill in some of the details, especially for things like storms that occur between LiDAR flights that are already ongoing. I just want to point out we've done most of our work in dry snow, flat terrain, and open areas, and now we're really testing that approach in more complicated terrain. I did skip one slide here, which is that after 2017 and 2020 and 21, that sort of proof of concept was enough to leverage a season-long campaign. So we did 6 sorties over 13 sites across the Western US. Those are all illustrated in white on the left. And that's one flight with the UAV SAR G3 aircraft can cover all of those sites. So it is a pretty efficient approach. We did that biweekly in 2020, then got shut down due to the pandemic, and completed another 10 sorties over a subset of 6 sites in 2021. And we had field teams deploying on the date of each overpass. And in collaboration with ASO, did LiDAR over some of the subdomains at a subset of the sites. Oops, let me go back here. Okay, so in more complicated terrain, initially we thought this wasn't going to work very well in places where we had significant melt. This is our test site to look at that. This is the Jemez Mountains in New Mexico. This is work by Jack Terracone, and Ryan Webb was the site lead. A big shout out to Noah Molotch for his snow depth sensors, which ended up being really key for this application. Main thing I want to point out on this slide is that all the areas in red are places where we lost SWE. The reason this is working is because this overflight was done early in the morning when the snowpack had likely drained or refrozen. So we could see that loss in SWE. The little bright blue area in the upper left corner is where there was a snowfall event at relatively warm temperatures. And you can see NOAA's snow depth sensors captured that increase in SWE in the blue area. And he had one depth sensor down in the place where there was no change, which showed that as well. So this just gives us some hope that that at least for the satellite observations early in the morning, that this technique has promise. There we go. Sorry, I'm having a little issue with things forwarding. Let me just back up. I'm going to just go in this mode here. Okay, so the basic idea here, again, is just that we're measuring this change in time of flight. Initially, we were worried that maybe stratigraphy would cause an issue because of the refraction of the wave at the different interfaces. It turns out that isn't a problem. It doesn't really significantly change the time of flight from forward modeling. On the lower left, you can see density and depth as a function of the phase change that we would measure. So we can deal with a snowfall change on the order of about a meter of heavy 30% snow before we get what's called a phase ambiguity. So the reason we're testing this approach is that NISAR is going to launch in January 2024, so a little over a year, and we'll be getting this data at 50-meter resolution every 12 days everywhere on the planet. I don't expect it's going to work everywhere, but in the places that it is going to work, it's going to provide a lot of useful information that can complement things like ASO, SNOTEL networks, and modeling efforts. With the upper right figure is if we go straight to a SWE inversion, the blue curve there is the phase change as a function of SWE, and the blue shaded area is the uncertainty for a pretty wide range of densities from 5 to 55%. So that's the uncertainty we want to try to constrain. We need to get a reasonable estimate of density to proceed with this approach. But I will point out it's less sensitive than the requirement on density for an altimetry approach because it's a little bit self-correcting because that wave speed depends on density. So just thinking a little bit about how much density varies in complex topography, there's been a fair bit of work on this. These are just some summaries from that CLPX effort. So a little over 600 snow pits from 2020 across those 13 sites. So we had a range of about 150 kilograms per cubic meter up to a little over 400. So almost a factor of 3. And that was during the period January to March of 2020, 2021. And so you can see these large variations with different snow climates. And again, just pointing out that this is mainly during the accumulation period. So a lot of great work's been done modeling density from an empirical perspective by Kat and Matthew Sturm and Tobias Jonas and James McCrite, as well as physics-based approaches like you've been hearing from the M3 Works group that's doing the ice snowbell modeling for ASO, other models like Snowpack, the Swiss model, Snow model, which is a model out of Colorado State University, and the Crocus is the French model. These are all approaches to estimating density in a seasonal snowpack. And if you haven't seen Mark Raleigh and Small's paper, they kind of look at this like how big of an uncertainty does snowpack density cause when we're trying to map basin-wide SWE with LiDAR. They found across a range of these empirical and physics-based models that they varied on the order of 30 to 100 kilograms per cubic meter, which could introduce an uncertainty in SWE on the order of 10% or more. And in particular, because the LiDAR depths like ASO are so accurate that once we get to about 50 centimeters of snow, it's really the density uncertainty that's dominating the SWE error, not the LiDAR error. That LiDAR error is so small, it's not really contributing. And it's really the density uncertainty that's contributing to the SWE uncertainty. But I just want to point out that a lot of these studies, the density observations are often in flat wind protected study sites. So we still are lacking big data sets of density in complex topography, in and out of different types of vegetation. And that's because density takes a long time to measure. It's not easy to do, and it's time consuming and expensive. So we've been thinking about how can we speed this up? How can we generate data sets of density to help contribute both to our radar applications as well as applications like ASO. And so I'm just going to share with you a little bit about some of those techniques. So I talked to you a little bit about how if we measure this time of flight through the snowpack with radar, that time of flight depends on the depth and it depends on the density because it depends on how fast that wave moves through the snow. In dry snow, that speed depends only on density. So if we measure this time of flight through the snowpack and we have something like ASO, an independent measurement of snow depth, we can constrain the depth and we know the time of flight through the snowpack, we can measure the speed, and then we can take that speed and invert it for a density. So this is our approach to trying to get at like big data sets of density so that we can provide tools to help improve modeling approaches for density. So I'm going to talk about two different ways that we've done this. The first is from the Cameron Pass site. This is work that Dan McGrath led. He was the site lead for SnowX at this site during the UAV SAR time series with a bunch of folks from his group. And as part of a project that he and Ryan Webb and I had funded by NASA. And we didn't have LiDAR at this site, at least not in terms of a time series. We didn't have the funding for that. And so what was done here is UAV observations, and many of you have probably heard of this structure from motion technique where you use many different pictures that are overlapping kind of in a photogrammetry kind of approach to get at a surface DEM. Similar to LiDAR, you take the snow on minus the snow off and you can get a snow depth. So Dan was flying UAVs, doing structure from motion on a regular basis at a relatively small scale. And at the same time, we deployed ground penetrating radar with this idea of testing this approach of using time of flight through the snow with an independent snow depth observation to get at snow density. So what does this kind of look like? The left figure are maps of the snow depth from those UAV flights. We first want to just make sure that our radar observations are making physical sense. So in the upper right is the radar image, and the red line is that identified snow ground interface. The antennas in this case are sitting right at the snow surface. So we can time that signal from the snow surface to the ground and back again. And if we use just the average density from a snow pit and look at how well the probe measurements as well as the radar compared to the structure from motion, we get a good agreement. So then we're confident that we can try to use that to estimate density by inverting for that velocity through the snowpack that the radar is measuring with the LiDAR. It requires that LiDAR. So we also compared this to in situ measurements of the permittivity, which is a measure of the electrical properties of the snowpack and kind of a more direct measurement of the velocity. We got decent agreement there. The main sort of takeaway here is that we did track the density. The red points there and the black points are the field measured density observations. So, you know, decent agreement on the order of the low end of those model comparison studies, but an approach that's really, really fast and rapid to cover large areas. So then we took this approach to Grand Mesa, where we did have LiDAR that was flown and processed by ASO over Grand Mesa during the 2020 campaign. And so I'll just kind of walk you through this figure. So in the upper left, on the right subpanel of the upper left there is just a bunch of pink lines, which is everywhere that we drove a ground penetrating radar on the Mesa. In this big grid pattern, you can see we didn't cover everywhere. This took place over the course of about 2 days and covered on the order of about 100 kilometers of area, with making these GPR measurements every 10 centimeters. So we have a measurement of the time of flight everywhere where there's pink, in addition to a bunch of tree areas that Ryan Webb skied through the trees with his GPR. And then we took the LiDAR and constraining the depth at each of these places where we're measuring radar time of flight, we invert for the density. So the density directly from this radar LiDAR combination is in the upper left figure. And then we distribute that using features from the ASO products like vegetation height, elevation aspect and things like that, and get this map of snow density that we verified with the snow pits. So you can see over this really flat area, there is a change in vegetation, but we have a change in density on the order of about 100 kilograms per cubic meter, about a 30% variation in density that we saw in the snow pits as well. And I'll just point out that most of the physically based models would have predicted a pretty similar density unless they had a wind compaction component to that densification model. So the things out on the west here are places where it's really, really windy and we're developing these big wind drifts, and that snow is getting really wind hammered. And on the right is where we're more wind protected behind tree islands and in the trees. So that produced a really big data set of snow density, but it's still limited to where we can actually travel on the ground with a radar. And that's fairly limited. It's hard to take those radars on steep slopes, and we can't do it everywhere. We can't do wall-to-wall mapping like ASO can. And so we went back to this interferometric synthetic aperture radar, which is called UAVSAR, flown by JPL. And we looked at the amplitude response, not just for one measurement, but for all 4 polarizations of the radar wave. And then using a machine learning algorithm, we tried to predict the density. It turned out that the snow pits were, even though we had 150 snow pits, that's not a big enough data set for a machine learning application. But with this GPR plus ASO LiDAR combination of densities, we had hundreds of thousands of density observations. That was enough to train a machine learning algorithm, which allowed us to estimate density from the radar directly. Again, just the caveats, I'll point out that this has only been done in this one flat location without a lot of topography. And so our next step is to start testing this in more complex topography and different vegetation types. So a lot of further work to do here, but we are getting encouraging results with a root mean squared error of around 20 kilograms per cubic meter for mapping snow density from this airborne radar platform, which should be possible from the satellite once it launches in January of 2024. So I'll just wrap it up because I'm about out of time here, but kind of just reviewed the INSAR approach a little bit, how it for measuring changes in snow water equivalent and snow depth is promising. We're still testing this in more complicated environments. We're trying to generate data sets that will improve density models, both for radar and ASO like LiDAR applications. Combining this radar with LiDAR or structure from motion is providing a new tool for mapping density spatially. And these spatial maps of density hopefully will allow model improvement in complex topography. And I'll just leave you with this last slide just to let you know that SnowX is really using an open data, open science approach. We have a various number of hack weeks. We're delivering a virtual bi-weekly series of hack weeks this fall that go over all of the 5 different aircraft and 7 different observations that were made as part of SnowX. So if you're interested, reach out to me by email, and I'll stop there.
Great, thanks HP. Always good to see the cutting edge remote sensing. Okay, do we have any questions? I don't see any. Oh, there's one.
I'm raising my hand.
Tom.
Hey, HP. So this is it's heartening, and actually it's great going back to Jeff's question. I can't remember if that was today or yesterday. It's all a blur. But Jeff Dozier's question and comments about having that independent map. But if I understand correctly, we're still constrained to a dry snow case.
Well, I think that the results that Jack Chericone has produced in the Jemez River, we are actually seeing loss in SWE that make physical sense. I didn't have a time to show the comparison to the change in fractional snow-covered area, but that pattern agrees quite well, but only when the snowpack is refrozen or drained. So that would require like an early morning kind of flight. And you know, in a flat area where the water's like pooling at a layer interface, I think we would still be challenged.
Yeah.
So I think mostly a tool to better understand precipitation patterns.
Right. Okay. All right, awesome. Thank you.
Thanks. And I'll answer Jeff's question in the chat. Thanks.
That'd be great. Okay, awesome. Let's move on. Next up, we have Graham Sexton from USGS, and he's going to be talking about snow hydrology and monitoring activities. And so do we have, there we go.
Yep. Thanks, Kat.
Yeah, no problems. And we can see your screen. It's just not full screen right now.
How's that?
Perfect. Off you go.
All right. Thanks, everyone. My name's Graham Sexton. I'm a research hydrologist with the USGS based out of Lakewood, Colorado. I'll be presenting today on some of our USGS next generation snow hydrology monitoring activities, and kind of presenting on behalf of a great research team that we have on this project. So, you know, a lot of this work is supported by this new USGS program called the USGS Next Generation Water Observing System, or NGWAS, as we like to refer to it. And so that program is really focused on, you know, providing some high resolution real-time data on water quality and water quantity in these focused integrated water science basins across the nation. And it's has particular focus on kind of providing increased spatial and temporal coverage of critical data sets with a focus on testing and maturing new technologies, really hoping to improve kind of the operational efficiency of the USGS and our ability to deliver, you know, needed data sets and kind of more cost effective and timely manner. And so these integrated water science basins that are being chosen, there's planned for 10 of them across the nation. There's currently 4 that are selected. They're shown on this map here. And sort of the goal being that each of these selected science basins will be somewhat representative of important, you know, hydrologic regions across our country. Across these integrated water science basins, there's sort of a focus on, you know, these core parameters of water availability, water quality that will be consistent from basin to basin. But at the same time, you know, with the regional focus, each integrated water science basin has kind of its specific focus topics that, you know, are regionally relevant science. So mostly what I'll be talking about today is for the Upper Colorado River Basin, which was sort of the second selected basin. And more specifically, the focus topic for that integrated water science basin being on snow accumulation and snowmelt processes, and particularly how, you know, snow contributes to surface water and groundwater availability and also salinity concentrations. That's kind of the regional focus of this basin. I didn't mention there's a plan for 10 of these basins. So there's 6 more that are planned to come. So Suzanne Paschke is sort of the PI for the Upper Colorado River Basin Integrated Water Science Basin. And I'm kind of leading up our snow hydrology monitoring activities. So that's sort of what my presentation will be focused on. I'll just say that, you know, our NGWAS efforts in the Upper Colorado are pretty wide reaching. We have focus on, you know, groundwater and, you know, new stream gauging techniques, but this presentation will just be pretty focused on our snowpack research. And so along with kind of the goals of NGWAS, our new snow monitoring is really focused on kind of developing, you know, new monitoring data sets, but also, you know, research and methods development to kind of, you know, push this type of monitoring forward for the USGS. You know, we all know that our snowpack, there's a substantial challenge in terms of being able to accurately characterize the seasonal snowpack because of its high spatial temporal variability. And so our efforts through this new program are focused on, you know, kind of threefold. One is trying to put out some new continuous snow monitoring stations. particularly focused on monitoring in environments that are not typically monitored. A second piece being, focusing on spatially distributed snow observations, be it on the ground, as well as UAS applications, as well, and airborne and satellite approaches as well. And then the last piece being really important. I'm not going to focus on it a lot today, but we're also focused on, new stream gauging techniques and new stream gauge observations, really trying to correspond with some of these snow observations to really support water cycle component evaluations. So our snowpack monitoring stations, I'll just briefly kind of mention our approach here. We have 2 stations that we've set up that we're kind of setting up as our test bed monitoring stations. So these are, full on snow mass and energy balance stations, but really kind of with the goal of being equipped to be able to take on and trial new sensors and technologies as they come online. So they're kind of these sites that we want to be equipped to be able to test out new technologies, have them well monitored so that we can kind of test new sensors as we go along with this program. The station shown in this picture is one of our sites in Winter Park. It's our Ranch Creek testbed station. And then we also have an additional site co-located with the NRCS Snowtel station at Berthoud Pass. And so really trying to, hopefully coordinate and collaborate with NRCS so that this type of sensor evaluation station can also support, their monitoring efforts going forward. In addition to these test bed sites, we have kind of a standard suite of continuous snow, mass, and energy balance stations that we're setting up in the Upper Colorado. Including those testbed sites, we have 15 planned monitoring stations. And then in kind of supporting this new continuous monitoring, we're kind of visiting these sites on the ground pretty regularly to dig snow pits, collect on the ground observations in order to assess how well these stations are performing. This is a kind of a laundry list of the different parameters that we're collecting at kind of these standard snow monitoring stations. So pretty comprehensive, the goal being that we'll be collecting all the data that would be, be able to be used in a physically based snow model, really focused on monitoring snow water equivalent kind of first and foremost, but also, snow liquid water content and some other unique parameters. All of the data we're collecting are hourly transmitted in real time and available in our NWIS database. Now, this is a map on the top right showing the distribution of our monitoring stations. And so we actually have 12 of these sites already installed across the basin. There's 3 of these that are not yet installed. We're still working on permission, but we're hoping to get this network pretty shored up before this coming winter to kind of really get this project going forward. And then the photograph on the bottom right is our site we set up a couple weeks ago on Independence Pass. So this is just sort of a visualization of our typical station setup, pretty minimal impact. We're not using any concrete so that we can kind of get it out there, set it up easily. And, hoping to be able to monitor in environments like this that are above tree line, very exposed to wind, not as typical of your typical snow monitoring station. We have a site co-located at Senator Beck with the Center for Snow and Avalanche Studies station up in the Alpine. We're co-locating some sites like this to be able to evaluate uncertainty and some of the meteorological variables that are measured, also be able to add some additional parameters at locations like this. And one parameter of interest that we're monitoring is blowing snow particle flux. And so that's the figure on the top left shown from this past winter. And then the graph on the bottom left is the snow water equivalent time series from this USGS station in orange. And then on the blue time series is the NRCS Snowtel station from Red Mountain Pass, which is about 1,000 feet lower in elevation in kind of the subalpine forest. And one of the things that really jumps out is you see this big, blowing snow redistribution, and potential sublimation losses that are occurring in January that really we're not seeing in our SNOTEL network stations. And then as well, we're seeing kind of this much later snowmelt timing because of this higher elevation and colder snowpack, up as much as 2 weeks later than the SNOTEL monitoring station, even though it was actually a pretty substantial dust year in this location. So this is kind of the type of variability that we're hoping to be able to capture with some of these stations, not necessarily capture wide-ranging spatial variability, but try to hit into some of these unique kind of environmental differences for snowpack monitoring stations. In addition to the continuous data that we're collecting at these monitoring sites, we're focused on also trying to collect on the ground spatial observations of the snow, particularly around these monitoring stations. They're going to be our goal of focusing on those areas. We can't monitor everywhere, but we can try to maybe hit on the ground at these locations pretty regularly, using traditional ground-based observations as well as sled-based GPR observations. And then we also have kind of a few UAS-based snow monitoring techniques that we've been employing, UAS-based LiDAR, as well as a software-defined radar and photogrammetry. So this is, we're really hoping that these spatial data sets, which will also be publicly available and a part of kind of delivering this new data to the community, we're hoping this can really help link these snow station observations with something more representative of a snow model pixel to kind of improve that type of modeling assessment. As a part of this NGWAS effort, we're partnering with CHASM and ASO to support ASO flights. Particularly for us, we're focusing on the Fraser River Basin because that's where we have some of our test bed monitoring going on. And we flew 2 flights this past winter in 2022, and hoping to kind of work out 2 more flights in 2023 this coming winter. And I'll just say this, for the USGS, these ASO data sets are, in the Fraser, but also really everywhere in the Upper Colorado and the study area. These ASO data sets are serving as these foundational science data sets for us that we can really use to kind of evaluate our ground-based methods, various remote sensing and modeling methods as well. So they're kind of, for us, that type of data set is going to just be tremendously valuable for kind of a variety of research-based snow monitoring and modeling approaches that we're going forward with. And then at the same time, we're working with ASO, and they're using our snow observations for some of their product evaluation and validation. So it's a nice synergy there that we can at the same time provide some on-the-ground data that can support the ASO efforts. And so this is my last slide. I just wanted to highlight one of our kind of more intensive campaigns we did this past winter. This was really our first winter of kind of going with this project. So I don't have this presentation doesn't have a lot of actual results. It's more based on kind of our plans, but this is a really unique data set that we collected in April around Berthoud Pass. So we had this study area kind of surrounding the NRCS SNOTEL station and our test bed monitoring site that kind of spanned this subalpine forest and alpine transition zone. And we were able to kind of get out there, and this is a photograph of our science team, and we collected quite a bit of on-the-ground data, geolocated snow probes. We have 23 snow core observations, 6 snow pits, and about 3 miles of GPR sled on the ground monitoring. And then at the same time, we were able to fly our UAS LiDAR photogrammetry and the software-defined radar. And then the best part is that we were able to coordinate it all, and we got the ASO flight for the Fraser to be on that same exact day. So I think this is going to be a really awesome data set. I'd love to connect with HP later, because it seems like this type of thing could be really valuable for his research. And yeah, we're looking forward to getting some of these results out there and out in the community, and hopefully we'll be able to continue to collect data sets like this going forward with this program. So yeah, thanks for the opportunity to be able to provide a little bit about our activities, and happy to answer any questions.
Great. Thanks, Graham. I think Jeff, you have your hand up there.
I just wanted to quickly echo something that Graham just said, and that is the synergy between the ground ops and the ASO operations. We've said this before, is not brand new, but it bears repeating that we absolutely depend on reliable ground observations to produce our products. So that's the NRCS networks and the CDAC network, et cetera, including manual snow courses. Every bit of snow depth, density, and SWE information that's out there and geolocated, we put to work, and it's invaluable. So thanks, Graham, to you and your team for that, and thanks everyone else in this community for maintaining all of those networks and observations.
Thanks, Jeff.
Yeah, absolutely. Ken, I see your hand up there too.
Yeah, thanks so much.
Great.
Nicely done. Nicely done, Graham. Really enjoyed that. So I have a self-serving question for you, and that is, I saw your Independence Pass location is now stood up. How about our joint interests in the Taylor Lake location? How's that coming, and is it already stood up?
It is not. Still haven't received permissions for those locations. So still actively pursuing it. And we really hope to be able to get in that location, because I think it would be a really unique site to be able to monitor. So
I'm doing a boots on the ground walk and talk with the lands officer of the Gunnison National Forest, John Hare, on Monday to get approval for some eddy covariance flux tower sites down in Ohio Creek. So I will be sure to bring up the Taylor Lake discussion on that walk and talk.
Awesome. Thanks, Ken. I would really appreciate that.
For sure.
Sounds great. Okay, so let's switch from Colorado. We're going to go back to California for a little bit. We have Luciana Cunha. I hope I got your last name right there. Talking about trends in the Sierra snowpack.
Okay, thank you, Kat. And I just want to reinforce what Jeff said. I don't do data collection, but I'm like amazed just watching your presentations, and I literally feel cold just looking at the pictures. So thank you for all the good work. I just use the data, and I really appreciate the work you guys do. Thank you also for inviting me for this presentation. Marco Bell told me a lot of good things about this group, so I'm excited to be here. And today, let me share my screen here. Let's be patient with me for a minute here.
No problem.
You are not seeing the right one, right?
We are seeing the presenters kind of. So we're seeing the next slide that comes up as well as the current slide.
Yeah, this Skype thing literally stays over my the part that I would be able to change that, so I can change that. So I'm gonna change the screen I'm sharing.
Okay.
Do you see
Perfect.
it right now? Awesome.
That looks great.
Okay, great. So today I'm going to talk about some analysis, some very simple analysis we did. We started it based on just curiosity. There is a lot that is being said about what is projected in terms of trends in the Sierra snowpack. But what we really wanted to do is to answer the question of what has already changed in the Sierra snowpack. And for the Californians one, we know that we have very strong variability in the weather in the West, and many people have probably already seen this map here, but I really like it because it really shows California as a hotspot, right? Where you see the most variability in precipitation, annual precipitation than other areas of the country. So we can really apply the same methods for water management in California that is applied everywhere else, because we have a very different climate here. So in some years we have a lot of snow and we are on a good position, and some years we do not. Here is just one picture of one of the stations. In April, we actually basically had no snow in that specific location, April 2015. The maximum amount of snow is that has actually snow water equivalent that has been measured in this location was 60 inches. So a huge difference. And this last year, the measurement here of snow depth was 2.5 inches, which was in the 4th percentile. So why do we use the April snow for water resource management? And the reason we have been traditionally using it is because that's when we expect snow to peak, right, in California, or at least in some locations of California, And so traditionally that has been used in water resource management to define water allocation. So as I said before, we have seen some numbers out there of projected. So SWE is projected to decline by 12 to 40% by 2050, depending on the emission scenario that we look at. But what we were really interested in looking at is what has already happened and how is it affecting our water resources. And just as a background, I will start with trends in precipitation. So this is basically the 8-station index in Sacramento, the station index in the San Joaquin Basin and Tulare Basin. So these are the 3 basins that I'm going to be discussing here. And you can see that there is some positive trend in precipitation for the Sacramento and San Joaquin Basin, while for the Tulare Basin, there's basically no change. So this is one component that will affect SWE, right? And in terms of runoff, we actually have seen decreasing runoff over the April-July period of time. So it's a little bit of a, we see increasing precipitation. However, we are seeing decrease in runoff. And the answer for that is probably because the volume is moving intact, right? So we are going to look a little bit more on this April 1st SWE. As you guys are all specialists on, DWR collects data manually in certain locations in California, and that's the data that we are going to focus on here. So we have 191 locations where we have more than 30 years of data, 106 locations where we have more than 60 years of data, and 55 locations where we have more than 90 years of data. So this is amazing. I think that's a very amazing work done by a lot of different organizations in California. We decided to focus on gauges that have more than 60 years of data, just because we want to make sure that we do capture the trend well. On the left here, you can also see the 3 different basins that we are going to focus our analysis at. So for the whole Sierra, and another important point is the percentage of watershed below each elevation. And we can see that Sacramento, basically almost the entire area of the Sacramento Basin is below 2,500 meters, while the San Joaquin and the Tulare Basin, you do have some area that is above that specific elevation. And here is just the contributing area for each one of the watersheds. So Sacramento Basin is a little larger. Okay, so some results here. I'm just showing the slope for the trend for all the gauges that I have for the 3 basins. So we can start to see some clear picture that, there is negative trends. They are not consistent across all the sites, but there are negative trends for elevations below 2,500. And we don't see much change for elevations for locations with elevation above 2,500. Now, if we divide it by each basin, Sacramento Basin, which has smaller elevations, do see sites with much more trend, up to 1 inch of difference in each 4 years, which is pretty significant. For the San Joaquin Basin, the trends are a little bit smaller, but it's still for the stations that are below 2,500, we do see some sites with significant trends. And the same picture for the Tulare Basin, where you can clearly see that there is a cutting point where you don't see, you still do not see the effects of climate change, but it's probably going to change in the future. So if we summarize everything and just calculate the average for these stations, we can see that we have a decrease of, in average, 5 inches in 60 years for the April 1st SWE in the Sacramento Basin, even though we have an increase in precipitation of 4.2. So our increase in SWE is really being masked by an increase in precipitation at this point. And the same happened for the other basins. But I think where it's really interesting to look at is how much volume are we actually losing because of that. So how much volume did we lose in a period of 60 years for each one of these basins? So if you look at the Sacramento Basin, we have displaced from the April 1st SWE 2.2 million acre feet of water. For San Joaquin, 0.38, and for the Tulare Basin, 0.35. What that means for California water management is that in a period of 60 years, we have lost basically 3 Folsom Lakes, or 9 Passaic Lakes, or even 85% of the Oroville volume. So it's a huge volume of snow that we are actually, or of water that we are not being able to use because it's being displaced from that April 1st volume. So as a conclusion, we have seen a lot of trends for sites below 2,500 meters. For sites above it, we haven't seen trends yet. It will come. We are pretty sure about it. And we have displaced from the April 1st SWE almost 3 million acre feet of water, which is a huge amount of water that we are missing. And how does it apply to ASO? It applies because we can't build reservoirs fast enough. We need to adapt much faster than we can actually build additional storage. So we really need to improve how we manage the reservoir, the storage that we already have in the state. And I think that's where ASO is going to be crucial, and I really appreciate the work that you guys do. And that's it. Thank you so much.
Great. Thank you so much for that. That was really interesting. Do we have any questions? If not, I have one. So the trends that you were observing below 2,500 meters, do you think that you could be also measuring, because you're focusing on April 1, do you think you could also be measuring some kind of seasonal shift? So maybe the maximums moved earlier or have you?
Definitely. And we are looking into it right now. Mm-hmm. But definitely that's what we are trying to show. But if you're shifting it and you're not changing the way the reservoirs are managed and operated, then you're losing it. So, that's the point that we are trying to make.
Gotcha.
Yeah, but definitely is a shift. It's not necessarily that this, and as I show, actually precipitation is increasing, right?
Yeah.
So it's not that we are losing the water, it's just that the water is, becoming available at different times. And because of our operation manuals, we can't use the storage in the reservoir at this time.
Yeah, that's a good point. So feeding that back into the operations. Yeah, that makes a lot of sense. Thank you. Okay, let's keep cruising. We have our last speaker, last but not least, Noah Molotch from Instar and University of Colorado Boulder. And Noah, we've been working with Noah for many years. And so I'm hoping he's going to tell us a little more about his CU Boulder product and how that relates to ASO and what kind of, the synergy between the two products. So go ahead. Oh, I think you're on mute, Noah.
Yeah, thanks for the introduction. And can you see the slides in presenter mode?
You're all good to go. No, we see the full screen.
Okay, great. So I think I wouldn't necessarily categorize this talk as a research talk, but more of an operations talk. And it'll be focused on a snow water equivalent product that we've developed over the past several years that fuses together ground observations with models and satellite-based remote sensing. And most recently, we've evolved our approach to consider ASO data, and it's been extremely helpful. So that's really the focus of this talk, is to let you kind of see inside the box, so to speak, of how we're interacting in real time with our model and with ASO data. And I want to acknowledge the colleagues that are listed here, in particular, Leanne Lestack, who's really the workhorse behind this effort. There are a number of collaborators that make this work possible. The California Department of Water Resources is the primary partner, but also the University of California and the Jet Propulsion Laboratory, as well as a number of local entities that are mapped out here on the right, as well as partners in other states that are contributing to this work moving outside of California. Very quickly, because I know most of the people on this Zoom call have seen our product before. It's a statistical model. So I think Jeff Dozier referred to it earlier in this workshop as a fancy interpolation. And I would agree with that summary. So the statistical model uses the observed snow water equivalent from the snow sensor network, which is shown by the black dots on the far left, as the dependent variable in the statistical model. And then the independent variables are listed here, and they're kind of run-of-the-mill topographic indices. And the fancy part comes in where we bring in historical snow water equivalent reconstructions, which are based on the physics involved in snow accumulation and ablation. And that model is constrained with satellite observations of snow-covered area. And Steve Margolis's group is really the workhorse behind those historical SWE estimates. And so those are brought in also as an independent variable to interpolate the sensors. And I think that's where really the value added is. And then in real time, once we generate the SWE map, we mask it to a real-time snow-covered area estimate from MODIS to give the final estimate of snow water equivalent, which an example is shown on the far right. And so just to kind of orient you first to the product for this most recent year, and then to jump in some of the ASO comparisons. So this is what the SWE distribution looked like. I'm trying to make you guys disappear so I can see my screen. For February and March of 2022, the large majority of the snowfall for the Sierra this year was in December. So it's a relatively uneventful change through February and March with some just kind of steady, subtle decreases in SWE. And then as we move into the beginning of April, you can see that steady decline continued. And then it shifted gears where we had a relatively wet April. So increases in SWE from early April toward the end of April. And as we then go into May, the SWE decline was evident, whereby the first week of May, we basically lost most of the SWE across the Sierra. So it was a very early meltout. These data are also shown in our SWE products when we deliver them to the stakeholders as % of averages. So the numbers inside each major watershed represent the % of average, that average period being from 2001 to 2020. And so because of the big December, we were starting off on February 1 above average. And then because of the lack of snowfall in what are historically pretty snowy months, the % of averages are dropping off into the 50s and 60s as we move toward the end of March. And then by the beginning of April, we're down in that 50% of average and below across the Sierra. And with the April snowfall, those were kind of sustained as % of averages through the month of April and then into the beginning of May. So what I really want to focus on here is kind of like how my perceptions of ASO data, how it's useful to us. And it's useful to us because it exposes, right, all the warts in this kind of modeling approach, or any modeling approach for that matter. So 2 examples are shown here for the Tuolumne and San Joaquin River basins in early February of 2022 ASO data on the left for both watersheds. And these maps aren't as polished as many that are shown in this meeting, because this is intended to kind of just show you what's under the hood of how we're looking at data in real time when we're in operations mode. Our SWE product is shown on the right, zoomed in. Of course, we're mapping the entire Sierra, but you can see the Tuolumne here at the middle, or sorry, at the top, and then the San Joaquin here. And if you look just by squinting, you can see that in general, the lower elevations, we're putting more SWE than ASO. And in the higher elevations, it looks closer, but if we difference them so that you don't have to actually do the math in your head, those same images are shown here, but different from each other. So the blue areas are those where we mapped greater SWE than ASO, and the red areas are those where ASO had more SWE than we had. And so the patterns of SWE bias that you see here in the Tuolumne and San Joaquin, 2 basins that on the sort of scale of the Sierra are relatively similar, the patterns of SWE bias are quite different. So if you develop a bias correction scheme, say in the Tuolumne, it's not going to be transferable even just to the San Joaquin, much less to the farther reaches of the Sierra, like up in the Feather, or down into the Kern, or to the east side. However, when you do have a robust archive of ASO data, there is a lot you can do in terms of bias correction. So this is some data that was shown actually in last year's ASO workshop by my former PhD student, Cunha Yang, a paper that's in preparation and soon to be submitted, where we've got 3 performance metrics of our modeling system: the R² for the top figure, the root mean square error for the middle figure, and the basin-wide percent bias for the bottom figure. ASO dates are shown across the bottom. And what I'm kind of emphasizing here is that if you remove ASO flights one at a time and use them as validation in kind of a mock real-time simulation, and ask yourself, how well could we use past ASO flights to bias correct a real-time SWE estimate, and then use that ASO observation to validate that estimate? You have an independent validation from the current ASO flight, and you leverage the past ASO flights to inform the bias correction. And so for these 3 performance metrics, I'll bring your attention first to the vertical red box plot on the top right for the R². That's the distribution of the R² values, this spatial R² of how well our model without the bias correction agrees with ASO. And then the 6 box plots in the different colors to the right of that represent the distribution of the spatial R² values against ASO for the different bias correction schemes. And so if you look at it as a whole, the light blue is what I want to bring your attention to. That's using a random forest model to perform the bias correction. It had a median R² of 0.89, so it's explaining on the order of about 90% of the spatial variability in the ASO data. That's a 10% increase in the median R² value of the model without the ASO data. And then if you look at the next metric down, the root mean square error, again, our model without the bias correction in red, and then you can see that RMSE value dropping considerably when we apply the bias correction, so down by 41% to an RMSE value of 69 millimeters. So significantly improved with bias correction when we have a robust archive of ASO data in a given watershed. So that's the luxury of being in a hindcast sort of research enterprise, of saying, theoretically, how can we develop the best algorithm for real-time application? But to look again under the hood of what we're actually doing in practice, is we're kind of flying by the seat of our pants, utilizing ASO data that's coming off the shelf in real time to us. We want to release our data within a couple of days after ASO does, so that it can be used by California Department of Water Resources in combination with a number of other data sources as well. And so this is a plot that's right kind of from that enterprise of Leanne and I on a Zoom call together, looking at what the data are telling us. And so these are SWE volumes and acre feet on the vertical axis for a number of different watersheds for February 1st of 2022. The blue vertical bars are from our model without any bias correction from historical ASO, because we only have that for the Tuolumne. The SNODAS is shown, that's from the National Weather Service in gray. The iSnowBow model results are shown in orange. The iSnowBow updated estimates are shown in yellow. And I do want to just clarify that this is from off the shelf when we're real-time mode. So if anyone has improved their model since that time, those wouldn't be represented here. So my intention is not to misrepresent anyone else's data. The ASO data are shown in the light blue. And what you can see here is that all the models are pretty consistently across all these basins overestimating SWE in early February of this past year. But we only have ASO data for the 2 watersheds. So we can't really do a whole lot in terms of bias correcting for other watersheds where we don't have the ASO data. And bias correcting in the watersheds where the ASO data exists isn't really that useful either, because the ASO data is there. So they don't, in those basins, our data isn't really needed. And then the next part of the story is when you go to mid-April. So on April 10th, a similar plot for major river basins of the Sierra, ASO data in the yellow, the iSnowBow in orange, SNODAS in gray, our model in blue. And for this time period, the modeled SWE products in general were underestimating SWE relative to ASO, except for SNODAS. So there seems to be a temporal component to the SWE bias that is emerging as we look at how things unfolded throughout the year. And at the time and currently, our belief is that the SWE model performance varies as the melt season progression alters the snow sensor representativeness. And we're heavily reliant on the snow sensor representativeness, which is a major liability of this kind of a modeling approach. But one of the things that we can do, and a potential bridge to estimating SWE in other areas that ASO isn't monitoring the SWE, is to look at the SWE performance by elevation band in situations where we have a lot of ASO data covering a number of different watersheds. So on the vertical axis is snow water equivalent in inches. And I apologize for the poorly labeled graphic here, but this is just from under the hood of our operational context. The major river basins we're looking at here are the Tuolumne, the Merced, the Kings, the Yuba, and the Cunha at different elevation bands. The ASO data is shown in blue, and there are four different ensembles of our modeling approach that are shown with the other vertical bars. So one thing that we're able to do in real time, because we have a number of different audibles that we can call with our model, is evaluate which audible aligns us best across different elevation bands and different watersheds with ASO data, which then isn't necessarily a direct bias correction, but it is a qualitative adjustment of our model to bring us more in line with ASO data. And some of those audibles can involve which snow-covered area data we're bringing into our approach, which ground data we're bringing into our approach, how we're treating zero values in our model, and which historical SWE reconstruction estimates are being used as an independent variable in our modeling system. Okay, so the final point here is to kind of get to what my sort of summary and recommendations are. And this is a selfish graphic to have at the end of the talk, because ASO data has been quite transformational, I think, across the realm of snow hydrology, and in particular for the kind of modeling work that we've been doing. So the quote of "the more I learn, the more I realize how much I don't know" is very apropos here. And what I'd like to see is that over time, we stop discovering new things that we don't know. And I think it will take a lot more ASO data to get us there. And when we think about the flow of the way that this kind of modeling approach has developed from data collection through data analysis and processing to training models, evaluating those models and tuning them, and debugging them, and then iterating with more data collection, ASO data has really been transformational in bringing us from sort of the problem formulation phase to the production phase of the kind of products that we're developing in our team. And so I want to thank the ASO team for all the effort there, and conclude and address any questions that may exist.
Great. Thanks for that, Noah. That was really interesting. Okay, do we have any questions? Jeff James, double hand raise.
Right. Yeah. I just want to make sure I jump to the front of the line with that.
Okay.
Noah, there was something that I noticed on the 3 metrics plot. We had the R squared and the RMSE and the bias, and I noticed it right before you finished on that slide, so I didn't quite get to form an opinion or a question around it. There was like one of the flight dates had pretty dramatically different metrics than other ones.
Yeah,
I was wondering if you could talk about that a little bit. I'm just kind of curious what that was, if there's something about that date or what.
Yeah, let me go. For some reason, when I'm in my share mode, it's not letting me toggle back through the slides. Hold on. So I will manually get us back to that slide. And then reshare. So I think you were referring to this slide, Jeff?
Yeah. And I guess, well, there's more than a couple, or more than one, I guess. So I'm looking at, I don't know, 5/17, 2014 in the top plot. All the R squareds are way low, or a lot of them are. And then, over in 2017, there's some really high RMSEs. I don't necessarily see a problem or anything. I'm just kind of curious what that is telling us about. I think this is because your leave one out date or something and predicting from that. Is there something about that date that doesn't relate to other ones or something, or what are we looking at there?
Yeah, good question. Well, even the model without the bias correction, right? So it's got a historical reconstruction that's combined with all the other variables. It's possible that may be where because that was a drought year, and it was late, mid-May. It may be that there were very few snow sensors still reporting SWE at that time, which, although it's interesting, there are a couple bias corrections that dramatically improved the R squared there. So I guess, unless Kohan's on the line, I would probably say I don't have a good answer for you there. But you can see 2015 that occurring a lot as well. Both drought years. Probably has to do with the relatively poor performance of the model when there's relatively few sensors with positive SWE values, SWE above 0.
Yeah, that makes sense as a working theory there. Anytime there's something that sticks out from the general pattern like that, I'm wondering if there's some information content there, either in a positive or a negative sense, about what can we learn from that date that tells us about how the relationships work elsewhere. So that's kind of where my mind was going with that. Anyways, thanks for.
Yeah, no, I mean, it's a good point. I mean, these are where you would look to make more improvements, right? So it's a challenge, but also an opportunity. Thank you for pointing that out.
All right. I think we've tired our audience out a little, but go and get a coffee and come back and let's finish it up with some good discussion. And as I hinted at earlier, there was a few questions asked earlier in the Q&A, indirectly, speaking to the RFC and how do we put these observations into models, and how do we know when it's going to tell us something useful or not? And so I would like to propose that we talk about some things to do with those topics, but I'm open to other topics that people want to raise while they're making their coffee. So let's go away and break for 10 minutes. Come back at 6 past the hour, and let's wrap it up. Welcome back, everybody. Not entirely sure how to start this discussion, but what I did do was poach some of the comments that we had earlier in the Q&A, and I'm wondering if I can share my screen somehow. There we go. Can you see my screen there? No, I'm just gonna hope that that's true. So these are some of the comments that some folks were making, and really talking, and this really spurred off from the RFC presentation that we had today, you know, about how do we use these highly accurate observations, you know, in a modeling framework, and recognizing that all models are different and have different assumptions and all of that. And so trying to bring that together in some kind of either a process, I think, perhaps is what people might be looking for, or what are the steps forward, or what questions do we need to answer to be able to make the best sense of this. So I'd invite anyone to speak. Jeff?
I'll jump in a little bit. So these were I lost these questions in my Q&A because I closed my Zoom between or over lunch, but thanks, Kat, for putting them back up. I think the first ones there were from Gus Goodbody, and then I think Josh Sturdivant chimed in with the second one there, and I saw a couple of thumbs up, at least, if not more emphatic than that, from a couple folks like Seth. Anyways, I think this is a really important question of how do we integrate, and one that, you know, full credit to the RFC folks grappling with this with this challenge in real time, and really what is an add-on to their normal workload. So huge thanks for that. And you know, this is an important question of if we've got an established modeling system that is based on a long period of record and a calibration procedure. If you swap driving data sets or state data sets, you know, what's the best process for retuning or recalibrating or making those models nimble to those data. This is certainly something that we're not going to finish today in an hour, and will be definitely a major component of our modeling workshop next month and beyond. But would love to get any thoughts folks have, kind of elaborating on the foundation that the RFC folks provided this morning. And I'd certainly want to invite, you know, Gus or Josh to elaborate on their questions here as well.
Great, thanks, Jeff.
I'll jump in. So it seems to me that that the exercise of updating existing empirical models is the greatest challenge with accurate snow water equivalent data. Building an empirical model from the ground up, based on the data themselves, is, I think, distinctly more manageable. We've seen that with some of the work in the various basins in California. And then at the other end of the spectrum lie the physically based models, which are expressly energy balance, and likewise what Noah and his team are doing with the reconstruction, and that's energy balance based as well. So, and being energy balance focused, then that really requires that the snowpack be accurate as possible. And so the scenario of the updates to existing calibrated models is there's just simply a tension there numerically. And we had several years ago in when we were still at JPL and working with the Western Water Applications Office, as well as well, when we first started working with the group that Seth Shanahan has been coordinating, that included the work with the CBRFC, and in that analysis, the first analysis suggested that at least at the CBRFC, Snow 17, the way it was being implemented, was modeling toward the real snowpack, and with excursions, of course, and it appeared that those excursions could be shored up by the ASO data in these offline runs. But now we've been expanding to more and more basins in the CBRFC domain, and it looks like some of those have some biases. At least it's certainly suggested. And so I think we need to put together an approach for this kind of this particular kind of effort that that acknowledges upfront that direct insertion without a bias correction to whatever modeling permutation space or subspace the snowpack, the model snowpack is headed toward, is dangerous business left alone, and that we really probably need to use a few years of data to at least start getting a handle on, is this basin's modeled snowpack biased relative to truth? And once we have that, then we move ahead. And I think what we've seen so far is with the ground up empirical approaches and with the physically based approaches, for the most part, the ASO data are really providing a substantial improvement in the central forecasts. The ASO data say nothing of the climatology of precipitation or forecasts of precipitation themselves, but updating the model state, it has proved to be really, really useful. Looking at it in these exercises, primarily with the RFC, that's where we seem to have a lot more scatter and a lot more, gosh, maybe it's helping, maybe it's not helping, we're not quite sure. And I think it really, until we have that well constrained to understand what those biases are, it's going to be a challenge. And likewise, looking at how you evaluate the success. I've been texting some with or emailing some with Mike in the background about his time series for from the CN RFC, and but I think that was another thing that Gus was getting at with his question, and Seth was following up on. All right, I'll shut
up. Noah, you have your hand up?
Yeah, I mean, I might be stating the obvious, but if the RFC's models calibrated over 20, 30 years of data, putting in better snowpack information doesn't necessarily mean that you're going to get better runoff estimates. And so that, is a cautionary thing to consider when as a data provider, you're delivering, but in theory, better SWE data. They put it in the model, the runoff, let's say it's not better, it doesn't mean that, shouldn't be a value judgment on the quality of the SWE data.
Yeah. Yeah.
Go
ahead,
go
Gus.
for it. We have pulled the reins off of you. You may speak.
Oh my gosh. Okay. Yeah, that's a great point, Noah. I mean, I totally agree. It's not the ability to fit this information into a hydrologic model that's then useful, you know, in these seasonal or shorter range forecasting areas. It's not a reflection of the ASO data. I don't think anyone's saying that. It's just its own. It's just to realize, you know, I think the full capability of what we expect from improvements with the improved SWE knowledge. That's what we're really getting at. And I just wanted to also qualify my point about the how do we use these amazing new data sets in our operational frameworks is one of the pieces. And I mean, I think Tom, you're absolutely right also about it's difficult for some of the existing operational models like the RFC model, perhaps, at least without building up some kind of a archive, you know, data set. I don't think it has to be 30 years, but it's certainly difficult with 1 or 2 years. And so it keeps pointing back to that, really. And I actually feel strongly about this, that like, there's no question to me that this is going to lead to great things, but it's going to take time, because I think we are limited even with our physically based models, because there's this other part of the coin here, which is, okay, so the physically based models may be more suited to take that information, but there's still an issue with those models as far as validation without, you know, having longer data sets of the nature that we want to feed them. So it's a problem with those models as well, unless you just buy off like, oh, it must be good. Okay, you know, someone said it's going to be better, so it must be. Like, the validation is a problem when we don't have you know, at least several years of ASO data to help both run and validate those systems.
Yeah, good points there, Gus. I think we've got Mike. We've been speaking about you, and now you can respond.
Yeah, Gus just kind of beat me to the point there that we're not trying to, you know, degrade the integrity of ASO data or make anything like that, any kind of overview or response like that. The goal of what we were trying to present was, you know, can we directly insert ASO data into a model and have that model perform well? And you know, I think in part we've started kind of answering those questions, you know, through what CD has done and what we've been looking at here at CN. As I mentioned, this is the first year that we've actually directly put it into the model to see the results, but we've been comparing snowpacks for years and been doing that research. So we kind of have an idea of, you know, maybe some of the biases in some of the basins. But you know, to elaborate on what Noah just said, and Gus too, you know, if this were, say, you know, a rainfall runoff model, you know, 5 to 10 years is usually an adequate amount of information to be able to calibrate off of. But because we're dealing with snowpack, and because that snowpack can vary so much from year to year, especially when we keep, you know, we're 3 dry years in a row, we need a variability of different snowpacks at different times of the year, you know, low snowpacks, high snowpacks. We need all that together to be able to accurately calibrate a model to that. So just taking 1 or 2 years, you can't really draw any sweeping conclusions from that in comparison to what you know, the ASO snowpack is. So it's, you know, it's an answer that no one really likes to hear, obviously, but it's just going to take years of data to be able to make comparisons and be able to try to unpack these differences and these biases between, you know, what ASO is estimating and then what we're estimating on our end. And of course, what we're estimating on our end is not static either. We're constantly, every day we're QCing a bunch of gauges and precip, and our precip estimates are not perfect, far from it. This is why we periodically throughout the winter go back and we pull in snow pillow data and snow course data, and we basically update our SWE and our models to more reflect what's actually being observed out there. So we know what we estimate is not perfect either. So just wanted to state that.
Absolutely, and thanks for making that qualification and sort of point. I think that point is really important, that we are on a journey here and figuring out how to squeeze the best information out of this data. Too bad for us, it's not direct insertion, in every single model. It'd be easier if that was the case, but it's not looking like that. And so, we have a little ways to go. I think it's a good point.
It may turn out that direct insertion works really well in some basins, but not in others. And we need to figure out why that is. As Scott showed on Monday, and I did a lot of the work behind that, where I was putting in the data. It worked very well this year for the Carson and the Truckee. But other years, next year it may not work well if we have a different snowpack, or maybe our snowpack estimates from the RFC are better, so it makes it appear as if ASO didn't help out as much. Again, the part that also makes this tricky is that the estimates from our end on the RFC end is not static. Some years we do better with estimating the snowpack, and other years we don't. So
I think that's a really important point, and it's something that I'd like to qualify something that Tom threw forward as well. Tom, you were speaking of biases as if they're static, and I recognize that was a bit of a shorthand to a much deeper conversation on your part. But I think that's a really important point, that there's the variability inherent in these systems means that a bias of a particular measurement, even ASO, which we're I think we can take it to be as a SWE truth because it's probably the best thing out there, but it is not perfect truth in every case or ever. So there's an ASO bias potential as well, and that's going to change over time. And so the question, it seems to me, is how do we take, every model is calibrated at some level or at some process. Some models more calibrated than others. In terms of the kind of the fraction of their product. How do we make sure that a calibration is robust in a non-stationary world? And if we're saying, okay, if by design a model seems to be or is dependent on this year being within the central third of the past 30 years of hydroclimate distribution, then that's going to struggle no matter what data we put into it. So how can we make changes either to the calibration process or model structure or some combination of those to minimize the dependency on that calibration and therefore on stationarity? And can we do that? I mean, I think there's a fundamental assessment of every model that needs to happen as to exactly what dependence on stationarity exists in different parts of it.
Yeah, good point, Jeff. And I think the stationarity concept applies differently to different parameters and different knobs in the model. And for some it may be wildly inappropriate, and others you may just be able to sneak it on through. We'll skip over to Marco, and then I think Noah will come back to you. So Marco, go ahead.
Yeah, thank you, Kat. And I apologize for not making the whole entire meeting and workshops that you guys have had. I always like to make this. This has just happened to be one of those years that I had a major conflict. But thank you for the opportunity to at least be here this afternoon. I'd like to comment a little bit on what I did before in the past in my previous tenure with Mercedes Irrigation District. We did develop a real-time HMS model, and we did do comparisons with various forecasts for the April 1st, April to July forecast on April 1st, And then at the end of July, we compare them to see how the runoff compared to the different forecasts that were available. And consistently in almost every year, the HMS model that used the ASO data directly as input into the model performed best. It wasn't necessarily first all the time, but the HMS model actually did best overall. We couldn't validate it, statistically significantly because we don't have enough data points yet. It was only a few years, but the preliminary indications is that it's really, really helpful. I like to add that it's not just a snowpack. I think there was, good mentions. We did find some bias in some of our basins, especially in the high elevation basins that produce a lot of water compared to the forecast that's given. But the snowpack continuous snowpack has to be adjusted with the monthly data that ASO provides. Otherwise, as you guys stated, it does drift, it does all kinds of things. So the data alone helps. However, you're right. It's not the only important component for computing runoff in real time for operations. And the snowpack may be great and your runoff may be off, but it's not necessarily due to ASO. I find that the soil moisture deficit is very important. I think that's what happened in 2021, where all the drought forecasts during the severe drought were higher than what we actually experienced. And the difference was that soil moisture. And that's dependent on the physical model itself and on how that is measured. And if that's really high, a lot of that water is just going to disappear into the soil and not show up as runoff. So I agree with a lot of that what's been said. I think it's important to expand a lot of what we're doing with soil moisture and try to figure out how the two combine in the different basins. So when you start getting multiple parameters that impact runoff, then it becomes a little harder to validate the models because you have to validate more than one thing. So anyway, I appreciate what you're doing, Tom, and I'm glad to be back. And it's good to see you guys. And you too, Kai. Thank you.
Great. Thanks, Marco.
Great to see you as well, Marco, except I can't see you.
Oh,
See you in person soon.
I don't have a button to put it on video. So my apologies.
Noah, you had something you wanted to contribute?
Well, it was kind of on accident that I pushed that button, but
too bad.
I think that the answer to whether or not any of these models can ingest the data is easy. The answer is yes. It's the amount of effort that's involved in going back through like calibration procedures and so on. And so it's kind of the effort versus reward calculus that each entity that wants to ingest these data have to go through. And that calculus depends on a lot of things, right? Like how big of a historical archive you have for them to play with. And importantly, and I hear this all the time from those that are potentially interested in using our data, what's the long-term security of the data flow moving into the future? So there is almost kind of a chicken or the egg kind of aspect to that calculus, right? But I think Gus and others and Mike can weigh in on that. The fact that you've gotten to the point where like somebody from an RFC is actively ingesting the data, that's a major milestone in my opinion in terms of like a research to operations kind of continuum.
Well, I'll add to that, Noah, real quick, Marco. No, I'm not sure if you were here on Monday when Dave spoke, but Dave Rosardo, DWR now has, they now have baseline funding for about 40% of the Sierra program, and they're going to be working toward the full build out of the program, 8 to 10, I guess 8 acquisitions per basin per year for all of the 18 Bulletin 120 forecasted basins. and then the chasm program, they are working towards trying to secure that operational sustained funding as well. So it really does seem to be happening, and I absolutely agree with you that the inclusion with the RFCs and these interactions with those teams, and it's, as you're saying, and likewise as Jeff was alluding to, this is not presently part of their job description, and so it's although I guess research, they are afforded latitude in research and improvements, which is fantastic, but it is extra workload for them, and it's really appreciated by all of us that they put that effort in. So at any rate, I think it's happening, and it's really exciting for the future. Marco.
Yeah, wow, that's awesome news. This is the first I hear of that, Tom, but I knew we were going to get there. Man, I'm so excited. And I wanted to say one more thing in addition to your ASO data. I know that I talked a little bit about, the forecastability, what do you call it? Knowledge, or, efficiency that you guys have. Efficiency is the wrong word. Well, accuracy, I guess I should say. It's actually pretty good, but more importantly for operations, we also need the variability of that forecast. Okay, so your variability is a lot lower, on your forecast than all the others. When I did it in Merced anyway, through that model, because that limits, our worst case scenario and on best case scenario in terms of inflows. We have to plan for that, and having 400,000 acre feet, variability in a reservoir is just, not operationally viable. So I really appreciate what you do, and it does help operations quite a bit down there. Thank you. Oops.
Thanks, Marco. Cody, I see your hand up. I'm excited to have you contribute.
Yeah, thanks. No, I appreciate the acknowledgement from Jeff and Tom and others about kind of what we've been thrown into, just kind of side development work related to ASO data and some of the requests we've had from users. We so badly would like to see, the direct insertion method just consistently improve our forecast. That would make our lives so much easier. Since we're putting the numbers out there and have to live with the verification results at the end of the season. So, we're always trying to improve our forecasts. But yeah, we do have plans to, bring this into calibration world on our end, and just continue to learn about everything we can about it. And, as others said, that we've strongly encouraged and pushed for more years, more flights over the same basins every year. And it looks like we're well on our way to that. So that's all I had.
That's great. I'm excited to hear that, you're carving out some time to do the calibration stuff. It is such a bummer that the direct insertion doesn't just magically work. So yeah, we're here to support that as well. Like, we really want to give you all the information you need to do this work that you're doing. And so if there's anything that you need as well, feel free to reach out to us. And we'll try and help you as best we can. I see Josh, you've got your hand up.
Yeah, Kat, I don't know that I have too much to offer besides what's been shared so far. I am really curious to see what a recalibration of SAC SMA and SNO 17 around ASO data means for improved forecasting. Because I think, as in many cases of modeling, maybe we are getting that right answer for the wrong reason, and snowpack in this case often can be that. But I think the other point I want to briefly discuss is that there are also other data assimilation techniques that haven't really been brought up today, but that offer a lot of promise. Direct insertion remains like a fairly crude DA method, and I think there has been research to show that the use of something like a particle filter, ensemble, Kalman filter can help a model, and especially a model that sometimes can be challenged when you are removing or replacing a lot of snow within that model and not otherwise accounting for the movement of that water through the system. And so I think there's research to be done there, and whether that's in sort of a SAC SMA lumped hydrologic model framework or WRF hydro or another distributed hydrologic model is yet to be answered, but that's one thing I did want to bring up.
Yeah, that's a great point, actually. And today's talks and for the last few days, we've really been focusing on the direct insertion, and there are other ways of doing this. And so it seems like we'll be heading down those pathways as we go forward.
Yeah, we're definitely exploring some of the Kalman filter approaches with Dave Gochis' group and the WRF Hydro. One interesting question is, the more kind of statistically aware assimilation approaches will allow the snowpack, or can allow the snowpack, to vary from what the ASO data says in order to accommodate the kind of variance in the model state space. And so I think it's probably more than just a conventional approach. If you have pretty narrow error bands on the assimilated parameter, does that give you enough flexibility in the assimilation routine in order to accommodate the flex and the other components that aren't being measured? That I'm not dismissing anything, but it's kind of an interesting problem that I don't think I've seen really discussed. And although I'm far from the expert on that, so it could easily just be my lack of awareness. But that's, I think, an interesting part of this is assimilating a parameter that we have a pretty tight measurement on versus, say, soil moisture, where we've got a couple of measurements, maybe, if we're lucky, and maybe just shifting the load of where the flex and the assimilation is in the water balance terms is another component that we should be looking at.
And we've talked about that in discussions in the workshop and other modeling meetings, and I don't think we've had anybody go through a proper analysis of it. But I think, Jeff, you're exactly right that it does, with the tightness of that measurement, it provides. I mean, it really provides a numerical rigidness that inhibits the flex in the rest of the model, which can be a wonderful thing, and it can also be a difficult thing. Joe, you had.
Well,
I mean, defer to you.
No. It's kind of slightly different. I mean, we've just been talking about direct assimilation versus using it in some softer way. And if I understood, I got a question for Noah, basically. That when I think if I saw one of your places where I think it was Tuolumne, you said, okay, so we'll bring in the ASO here to nudge or adjust or assimilate or whatever the model. And it doesn't snap right to the ASO, so it's not a direct assimilation. I think you were 7% different still or something. So I didn't know if you wanted to, wanted to share more about how that is getting used, since it didn't look like it was like a direct insertion, so it would match.
Yeah, so that ASO flight is actually not used at all. So it's kind of going through a theory. Imagine you're at a date. Today's not a great date because this is like the lowest point of the snow season. But let's say
I can imagine April.
Do it in South America.
Yeah.
Let's say we're in March 1st of next year, and I run my model based on the SNOTEL and all the relatively coarse information I have to get a SWE estimate in the across the Sierra, and I get SWE estimates for the Tuolumne. I can take the 60 or whatever number of ASO flights that have occurred prior to that date, which also coincide with when I've run my model.
Right.
And I have spatial maps of my model error for all those historical dates. I can, for each of those dates, create a model of that SWE error, which once generated can be used as a bias correction for the current date. So in theory, you have 60 options from the past of bias correction models to apply to that current date of March 1. So then you'd have to do some kind of an analog analysis to decide which one of those.
Like which ones have a spatial pattern that's relevant or something.
That's most relevant.
Cool.
And that's what that exercise.
Well, that sounds.
Then
yeah.
you flew March 1st, so I can use that date because it didn't go into my model as an independent validation.
I see what you're saying. Yeah, cool.
Yeah.
Okay, I understand better.
Yeah.
But it gets to this whole bigger question of, I mean, maybe I'm just old, but the models are never going to match the data, right? Nature is more complicated than any of our models. So this question of how do you use real measurements, that's a neat way to do it, I guess, as opposed to like direct insertion.
Yeah, thanks for explaining that, Noah, and asking that question, Joe.
Hey, Noah, I was going to actually say that, in your presentation, you mentioned that, there's no reason for you to then produce that value because you have the ASO data already. And that's, we consider that to be, closer to truth, so to speak. And maybe I misunderstood what you said, but to me, actually, I think there is a reason. And the reason is that your model actually has a longer historic record. And the fact is, the year-to-year variability in many times can be more important than this like last drop measured approach, as far as with our current modeling systems anyway.
Yeah, I agree with that. I think there was a nuance that I was getting at, which is that if I bias correct in the Tuolumne on the date that ASO flew, then my historical runs, like it's pushing my model out of where it had been historically, and it's being trained to match ASO on that date. So it doesn't really provide a nice ensemble member for those considering a number of different SWE estimates, because it's being nudged to match the ASO, and the ASO exists. So I agree with you, Gus. Like, we provide our SWE data coincident with the timing of ASO data routinely, but it's relatively independent from the ASO data itself. And if we were, that's why, like in that plot that Jeff Deems asked me about, each ASO flight is pulled out to be independent and therefore used as validation. Because if we were letting the ASO data enter into the modeling activity, it's cheating. In other words, it's one way to kind of think about it, right? We want to simulate, like, how good could we do if we didn't have ASO, and do that on dates when we have ASO, so that we can use the ASO to validate and answer that question: how well can we do without ASO?
Yeah, certainly connecting back to, that's one thing you provide is a connection, right, to times when we don't have ASO, and that still seems like a very worthy and important direction right now, how to actually stitch the new tech with the old tech, so to speak.
Yeah, just one last point on that. The literature is actually pretty consistent on transference of sweep patterns in time being relatively doable, whereas transference of sweep patterns in space is pretty much not doable with any sort of adequate measure. And what I mean there is from a statistical standpoint. If you're going to use any kind of statistical modeling, sweep patterning in time is a much more tractable problem than sweep patterning in space. And that's why my last recommendation was like, we need archives like the Tuolumne in a bunch of different climatological and topographic environments, like preferably all over the globe.
Because like a model like yours relies on having that set of eigen coverages or something, right? That, you know, the type, the systematic coverages that might exist.
Yeah, once you get to like a decade's worth of data with like 60 flights in a place as variable as the Sierra, you got a lot of different conditions covered there with all those ASO flights. I mean, I don't know what that cost over the, you know, that 10 years, but and you know, but if you have, you know, the Feather and maybe the American and then the Tuolumne and then maybe the Kern, you might be able to start to, I mean, we've only been working with the Tuolumne and then trying to go across the whole Sierra. It's like, well, duh, you're not going to be able to do that. But if we had like some ensemble of representative basins with Tuolumne-like archives, then we might be able to actually do the whole Sierra.
Okay, I'm going to jump in.
Do it, Jeff.
Yeah. As I posted in the chat, it seems like our discussion has focused on you know, just a little bit of what we talked about today. So let me put in a plug for the importance of the stuff that HP Marshall has presented. I am still pretty skeptical about the density modeling that we're doing. I agree, you know, with Tom's assertion that in the original ASO paper that most of the variability in SWE comes from variability in depth. But now that you nail down depth, then really the remaining uncertainty is the variation in density. And part of the problem is that we don't have density measurements in very many places. It takes a long time to dig a snow pit, and the measurements of depth and SWE at the pillows are all on flat ground. So you're not capturing any variation of density with topography. So, but the idea of using, so interferometric SAR, the phase shift, the interferometric phase, is a product of both a depth term and a permittivity term, and permittivity just varies with density. So it's essentially you've got a depth term and a density term, and they're both unknowns. And therefore, the way you retrieve depth from interferometry is you assume a density. And then the uncertainty in that density propagates directly into the uncertainty in the estimate of depth, and therefore into the estimate of SWE. So, to me, when I look at the various papers on snow models, they all go back to Kojima 1969 in terms of how they get density. So you really don't have these different models of density. You have one model, and then it's been incorporated into everybody, into all the other models. So it would seem to me that there's an opportunity here to really advance the science of snow by actually enabling a way to get a wide spread measurement, a real map of densities over pretty rugged topography. And, I think we might be able to get that with NISAR. There's a project I'm involved that might be able to get this from an airborne mission. And it would seem that in terms of ASO contributing to the science, this is a really fruitful path.
I'll jump in and say yes. I absolutely agree with you, Jeff. In fact, the KU band unit that was up at the Mammoth Mountain site, HP and I were involved with that, and my efforts in that were directly towards being able to have these supplementary measurements, and and HP is not going to escape us with respect to NISAR for those times in which we can get at these independent measurements of density. I think what we have seen, at least in the relatively longish record now of density modeling, is actually pretty good, and I think it plays out implicitly when you consider the results from the forecasting that comes from the data chain. But I absolutely agree. I still want to see that additional set of measurements, spatially explicit, that we can have to help us understand any of the shortcomings that we have, and to continue to improve that density field. I don't know if HP is back there. There he is. There you are.
Yeah, I can comment. I mean, I think one challenge with NISAR that still is going to require definitely a modeling component is that the density part, if we use NISAR with LiDAR, since it's not measuring a total travel time, but a change, it's going to tell us about how the density changed. So each overpass will be able to make maps of the change in density when we have coincident LiDAR. And so I think there's a big opportunity there to use that to try to understand how it's changing, like after a storm event and over time. And then with these more airborne sensors and ground-based techniques where we have the bandwidth where we can measure that total time of flight through the snowpack, then we can get at bulk density. So yeah, I think there's some opportunity with some of the IAPs that Tom, you're involved with as well, that we should be trying to align those radar observations with LiDAR whenever we can.
And I've prepared the team that the time is coming that the door is going to have a radar, at least one radar unit in it. Awesome. I know they don't get supremely excited about that necessarily.
Why not? I'm not much of a radar guy, but the forest is going to get involved here in many of our basins.
Yeah. Yep.
Yeah, and then
I was pretty HP. I've seen kind of the evolution of the L-band work, obviously being involved in SNOAX over a number of years now, and I'm like continually impressed at how that fusion is coming along. And it excites me from a model constraint perspective. And I think I would argue that that's how we should be thinking about this, is taking the density models, whatever they are, whatever it is, and constraining it using observations like the L-band interferometry, and especially in the new snow density is such a hard thing. And so if we can get, a constraint on just the new snow density change, it's huge. That's awesome. And what fraction of the total bulk snowpack that is. I mean, Cat goes to hours of effort to try to pin that down, interpolating between when the last snow course measurement was and what the model's saying and what the snow pillows are saying. So that's a huge challenge for us. Another thing that we need, especially being concerned with snow melt, is the ability for this to work in wet snow. And by this, I don't mean specifically radar, I mean the density estimation package. And one question I have is, and maybe Jeff Dozier can speak to this, how continuous is our density estimation physics in the models across dry snow densification and wet snow densification? Can we use INSAR to constrain the dry snow part of the model and then expect that improved performance to persist as we get into wet phase?
Yeah, so what happens, two things happen when you get water and snow that screws up interferometry. One is that there's some absorption from the water, so your signal degrades a little bit, and then also what happens is even the real part of the refractive index increases with water in the snow, and therefore you get a much bigger part of your signal just comes back from the surface. Whereas interferometry, with dry snow, there isn't much of a reflection from the surface, and at the longer wavelengths especially, there's not much volume scattering from the pack itself. And so therefore, with dry snow, most of your signal is a radar beam that passed through the snowpack and came back through the snowpack. And with wet snow, that's no longer true. Now, I think the thing that maybe hasn't been investigated very well yet is, wet snow, dry snow it's not a binary classification.
Right.
That, sometimes snow has a little bit of water in it. There may be layers in the snowpack where there's a short thickness of water, or you have a ripe snowpack that is draining and is wet. You get around some of these things by a lot of times. The radar people want to fly at like 5 or 6 in the morning to try to get at least some of that surface water near the surface has refrozen. But those are kind of the considerations. So having an infinitesimal amount of water in the stove doesn't screw you up. But having like a volumetric water content of 10% throughout the pack then most of your signal is just going to come back from the surface.
Yeah, we've been finding like we can deal with about 2% liquid water content, which on slopes at night, if you're on a slope and the water is draining laterally down slope, we tend to, at least from our field sites, see that liquid water reduced to a couple percent, and then refreeze a little bit at the surface. And so things can kind of work in that scenario. But But yeah, water pooling at a later interface and getting up to 10%, I don't think that's a place where the radar piece is going to be very useful.
Yeah. Now, the one thing that really does happen is the radar can tell you where the snow is wet. You know, so in terms of comparison, say with your snowmelt models, to really identify the places where in fact active melting is occurring, and so so yeah, when we think of multispectral, we really should go from the visible out through the you know, out to key band or something.
Absolutely.
Yeah.
All right. Well, we've kind of reached our little end of our discussion time. And I would really like to thank everybody that contributed to the discussion. It was really interesting. And it was lots of things to talk about. I'd like to also thank everybody that spoke today, and the people behind the scenes that helped me chair this session. Thanks to you all as well. Hope everyone had a good time, and I'm going to pass it off to Tom for the final word.
Awesome. Thanks, Kat, for handling it today, and thanks, Jeff, for handling it yesterday. To Liz and Kate and Molly in particular in organizing the workshop. And I want everybody to know that for the most part, they had organized it to be in person. So they went through the effort of organizing it to be in person, and then had to go through the effort of organizing it online. And so hopefully that we can just freeze that effort for in person for next year, and not duplicate that. I just again, I want to thank everybody for participating. We'll figure out how many individuals came and interacted in the meeting over the 3 days, but it looks to me like it was about 100 people, if I got that accurately, and really important people in really important sectors. And your interactions are incredibly important. And going back to what I said in my talk yesterday and what I've said before, my sense when I got recruited to JPL to do something along the lines of building ASO was really that the resources were there, and this was something that I could do for our community. And this team that we have thinks about ASO as a community resource, and not just on the water management side, but also on the science side. And of course, we are taken over more and more by water resources and less in the research side than we used to be. But nevertheless, as this last discussion just evidenced, we continue to be involved and interested in research. And so having all of you here is incredibly important to that. So reminder that we're working toward dates in the second half of October. Jeff, have we gotten any clarity on that yet? I know that I know that it does conflict with the Who concert in Sacramento, which is a problem.
That's the biggest challenge right now.
Maybe we should just have the meeting in Sacramento accordingly. Yeah, that's going to be a great meeting to have, and obviously we have a lot more to discuss, and just looking at the various paths out in front of us on the modeling front. So let's see. I think that is it, other than just a reminder that that the number of flights and the number of basins. Gonna terrify the team again, but the number of flights and the number of basins is increasing again this year, pretty substantially. We are likely to be flying 3 of our own aircraft, and then doing work with our subcontractor and partner, Quantum Spatial. And I think what we've been talking about in terms of building these legacy data sets is only going to continue to grow. And if you have research, either research on the pure science side or technology or on water resources side that you really want to pursue with us, please let us know. We can help to, just as we did with the interaction on the UAV SAR flights with SNOX, we can always try to bring that into the mix. And DWR and the CWCB and as you've seen in the various operational water managers here, continue to be very interested in supporting the science moving forward to ultimately help on the water resource exploration. So at any rate, please do reach out to us if you have any thoughts on what you'd like to do, and we will be there to bring it into play as best we can. Unless I've forgotten anything. Have I forgotten anything? I'm seeing nope. All right, well, thank you all again, and I will bring this ASO workshop to a close, and next year we hope to see you in person. Thank you all.
Thank you.
Thanks.
Bye.
Thank you.
Bye.